This is the world of the Late Cretaceous, somewhere between 70 and 80 million years ago, when the last chapter of the Age of Dinosaurs was being written in the rock and bone and breath of a world that would soon be changed utterly. And in this world, in this ancient South America, whose bones we can still find today embedded in the dusty hillsides of Patagonia in Argentina, there moved a predator unlike anything that has ever walked before or since. Its name, when scientists finally gave it one, was Carnotaurus. The name comes from the Latin caro, meaning flesh or meat, and taurus, meaning bull. So Carnotaurus means, quite simply, the meat-eating bull. And when you see the reconstruction of this animal, when you look at the bones that were pulled from the Argentinian rock in 1984 and understand what they represent, the name makes every kind of sense. Because Carnotaurus was not merely unusual, it was something that should not, by any reasonable expectation of what a large predatory dinosaur ought to look like, have existed at all. Picture it slowly, the way you might let a dream take shape behind closed eyes. Picture a predator roughly 8 meters in length from the tip of its snout to the end of its tail. Not the longest dinosaur that ever lived, not the heaviest, but a creature of extraordinary compactness and muscular solidity, built the way a sports car is built compared to a cargo truck. Everything arranged for speed and impact rather than sheer, overwhelming mass. The hind limbs are long and powerful, proportioned in a way that suggests a runner, a sprinter, an animal capable of covering ground with a quickness that its Cretaceous competitors could not easily match. The forelimbs are tiny, so tiny as to seem almost absurd, reduced down from the powerful grasping arms of ancestral predators to something closer to vestigial paddles. 4 stubby fingers folded against the sides of a body that simply has no use for them. The tail is long and muscular, held straight and level behind the body, providing balance and counterweight as the animal moves. But it is the head that stops you entirely. It is the head that makes Carnotaurus something you will remember long after every other piece of this story has blurred with sleep and warmth and the comfortable dark. Because the head of Carnotaurus, that magnificent and deeply strange head, was unlike the head of any other large predator that has ever been found. The skull was short and deep, almost blunt in profile, with a height and a width that looked compressed, squarish, nothing like the long, low wedge-shaped skulls of its distant cousins, the Tyrannosaurs, or the elongated hunting instruments of the Spinosaurids. And rising from the bones just above the eyes, curving outward and slightly backward with a sturdy, confident solidity, were 2 genuine horns. Not ridges, not brow thickenings, not vague, bony protrusions. Actual horns, roughly 30 centimeters long in life, stout and keratinized, the kind of structure that you associate with a bull or a bison or a longhorn steer, planted on the face of a large predatory dinosaur, as though evolution had decided partway through the design process to see what happened when you combined a meat-eating theropod with the spirit of a fighting bull. This is Carnotaurus sastre. The species name honors Don Angel Cabrera Sastre, the rancher on whose land in Patagonia the specimen was found. And the story of that discovery, of the bones in the hillside, and the paleontologist who recognized their significance in the years of careful work that followed, is part of the larger story of this animal, a story we will come to in its own time and in its own gentle way. But first, before the discovery and the science and the debate and the wonder, we need to sit for a while with the world that made this creature. Because no animal can be understood apart from the land and the time that shaped it. And Carnotaurus was shaped by forces so particular and so fascinating that to understand them is to understand something deep and true, about the way life works. Let yourself settle more deeply now into wherever you are resting. Feel the support beneath you, the warmth around you, the slow rhythm of your own breathing. And let the story carry you gently forward, the way a river carries a leaf, without effort, without resistance, just the easy drift of a mind releasing its hold on the day and opening to something older and stranger and quietly wonderful. The Late Cretaceous of South America was a place of profound isolation. This is perhaps the single most important fact about the world that Carnotaurus inhabited, and it is a fact that shaped every aspect of this animal's biology, its anatomy, its hunting strategies, its relationships with the other creatures of its ecosystem, and its evolutionary trajectory over millions and millions of years. South America in the Late Cretaceous was an island continent, not in the metaphorical sense in which people sometimes describe isolated cultures or remote communities. Literally an island, a great landmass entirely surrounded by ocean, separated from North America by a seaway that would not finally close until the Pliocene epoch, roughly 3 million years ago, when the formation of the Isthmus of Panama joined the two continents and triggered one of the most dramatic biological events of recent geological history, the Great American Biotic Interchange. But in the Late Cretaceous, that joining had not yet happened. The seaway between North and South America was open and wide and full of marine life, and no dinosaur, no large land animal of any kind could cross it, which meant that South America was developing its own evolutionary experiment in complete independence from the rest of the world. The dinosaurs that had colonized South America in earlier geological periods, during the Jurassic and the early Cretaceous, when land connections still existed in some form, had been evolving on their own for tens of millions of years, taking paths that no animal on the other continents was taking, developing body plans and hunting strategies and ecological relationships that were unique to this vast, warm, isolated landmass in the southern hemisphere. The result of this long isolation was a fauna, a collection of species living together in a given place and time, that was unlike anything else on the planet. On the land masses that would become North America and Asia, the Late Cretaceous was the age of the Tyrannosaurs, of Tyrannosaurus rex and its relatives, massive predators with enormous skulls and powerful bone-crushing jaws that dominated their ecosystems through sheer crushing force. In South America, the equivalent ecological role, the role of large apex predator, was filled by a completely different lineage of dinosaurs. It was filled by the Abelosaurids. The Abelosaurids are the family to which Carnotaurus belongs, and they are one of the most fascinating and least well-known groups of large predatory dinosaurs in the entire Mesozoic record. The name Abelosaurid comes from Abelosaurus, a genus discovered in Argentina and named for Roberto Abel, who was the director of the Provincial Museum of Cipolletti in the Neuquén province of Argentina at the time of the discovery. Abelosaurus itself is known from relatively incomplete material, primarily a skull, but it gave its name to the entire family of large predatory theropods that share a distinctive constellation of anatomical features, setting them apart from all other large predators. What makes an Abelosaurid? The question is worth asking slowly and carefully, because the answer is so striking. Abelosaurids were, as a group, characterized by deep, blunt skulls with proportionally short faces, by greatly reduced forelimbs with fused and highly modified bones that in some species were almost entirely non-functional, by generally robust bodies built more for power than for speed, and in many species by elaborated ornamentation on the skull in the form of horns, crests, ridges, and bony knobs. These animals were not trying to be Tyrannosaurus rex. They were doing something completely different, operating on a completely different set of biological principles, having arrived at the role of large apex predator through a completely separate evolutionary pathway. And the result was, by any measure, one of the most visually extraordinary groups of animals that the Mesozoic produced. Carnotaurus was the most extreme expression of the abelosaurid body plan in almost every regard. Its skull was shorter and deeper relative to body size than that of most other abelosaurids. Its forelimbs were reduced further than in most of its relatives. Its horns were larger and more dramatic than anything seen in any comparable predator. And yet, for all its extremity, for all the ways in which it pushed the abelosaurid design to its limits, Carnotaurus was not a freak or a failed experiment. It was a magnificently successful apex predator that occupied the top of its ecosystem's food chain for millions of years. Evolution does not produce failures that persist for geological ages. What evolution produces is solutions. And Carnotaurus, however strange it looks to our modern eyes, was a solution to the specific challenges of being a large predator in the late Cretaceous of South America. To understand those challenges, we need to spend some time with the land itself, with the Patagonian environment of 70 to 80 million years ago, because it was that environment, with its particular combination of climate and terrain and prey animals and ecological pressures, that selected for every unusual feature of the Carnotaurus body plan. The Patagonia of the late Cretaceous was a very different place from the cold, windswept, semi-arid region that modern travelers visit today. In the Cretaceous, the global climate was significantly warmer than the present, with no polar ice caps and a more even distribution of warmth across the latitudes. What would become Patagonia lay at a somewhat lower latitude than today, and the climate of the region was humid and temperate to subtropical, with extensive river systems and broad floodplains supporting dense vegetation and large populations of the enormous plant-eating dinosaurs that would become the prey of Carnotaurus. These plant-eating dinosaurs were, for the most part, titanosaurs, a group of sauropods, those great long-necked giants that had diversified enormously in South America during the Cretaceous and become the dominant large herbivores of the southern continent. Some titanosaurs were of truly staggering size. Patagotitan majorum, discovered in the same general region of Argentina that yielded Carnotaurus and described in 2017, was one of the largest animals ever known to have walked on land, with an estimated mass of 70 metric tons and a length of perhaps 37 meters. These were the animals at the base of the food web, consuming enormous quantities of vegetation and converting plant matter into animal biomass that then supported the predators higher up the chain. And Carnotaurus, compact and relatively swift by the standards of large theropods, was adapted to hunt them. Now, hunting a titanosaur, even a juvenile one, is not a simple matter. These were animals of extraordinary mass, armored in some species with bony osteoderms embedded in their skin, capable of delivering devastating blows with their long necks and heavy tails, and surrounded in many cases by other members of their herd who could collectively defend the young and the weak against an attacking predator. A Carnotaurus approaching a herd of titanosaurs was not approaching easy prey. It was approaching a challenge that required every advantage that evolution had provided it. Every specialization of its remarkable body, every trick that millions of years of selection had built into its hunting repertoire. And to understand how Carnotaurus met that challenge, we need to understand its body in much more detail than we have so far considered. Let your breathing slow a little. Let the image of that ancient floodplain settle in your mind. warm and green and impossibly distant, while we take a closer look at the extraordinary animal that moved across it. There is no rush. The story has been waiting for 70 million years. It can wait a little longer while you find your comfort. The skull of Carnotaurus is where any serious examination of this animal must begin, because the skull is where the most immediately striking and most scientifically fascinating features of the animal are concentrated. The skull was discovered in a remarkable state of preservation in the original Argentine specimen, and what it revealed to the paleontologist José Fernando Bonaparte, who described the animal in 1985, was something that had never been seen before in any known theropod dinosaur. The skull was short, deep, and wide, giving it a profile that looks almost compressed when compared to the elongated, streamlined skulls of most other large predatory dinosaurs. In length, the skull of a large adult Carnotaurus was roughly 60 centimeters from the back of the brain case to the tip of the snout, which sounds substantial until you remember that this was attached to an animal 8 meters long, meaning the head was proportionally quite small relative to body size compared to the enormous skulls of tyrannosaurs. But what the skull lacked in length, it more than compensated for in height and in the overall impression of power and unusual design. The two horns above the eyes are the feature that defines the animal in popular imagination, and they deserve careful and extended description because they were not simple decorative structures, but complex bony outgrowths with a specific geometry and a specific arrangement that tells us something important about their function. Each horn arose from the lacrimal bone, which is one of the bones that forms the region around the eye socket, and grew upward and outward from this anchor point, curving slightly backward and laterally, so that the tips of the horns, when viewed from the front, pointed slightly away from the midline of the skull. The horns were not symmetrical in the strict sense, but were roughly mirror images of each other. And in life they would have been covered with a keratinous sheath, the same biological material that covers the horns of modern cattle, buffalo, and rhinoceroses. This keratinous sheath would have added to the length and presumably to the smooth, hardened surface of the horn, beyond what the bare bone reveals. The size of the horns in the known specimen, extrapolated to include the keratinous sheath that has not been preserved in fossilized form, suggests that they were impressive structures in life, roughly 30 centimeters in length or perhaps somewhat more, which on a skull of 60 centimeters made them a significant proportion of the overall head dimensions. When Carnotaurus faced another animal, whether a rival of its own species or a potential prey item or a potential predator, those horns would have been immediately and unmistakably visible, projecting forward and slightly outward in a display of whatever they were communicating: size, danger, identity, or simple biological strangeness. What were the horns for? This is the question that has occupied paleontologists since the moment the skull was first fully prepared and examined, and the honest answer, which is the only truly satisfying kind of answer in science, is that we are not entirely certain, but that we have several well-reasoned hypotheses that the evidence can support or undermine to varying degrees. The possibilities that researchers have seriously proposed fall broadly into three categories: display and species recognition, intraspecific combat between members of the same species, and some role in prey capture. Let us take each of these possibilities gently and in turn. The display hypothesis is perhaps the most immediately intuitive. Many living animals carry elaborate structures on their heads that serve primarily as visual signals to other members of their species, communicating information about the bearer's identity, sex, age, health, and social status. The horns of many deer species, for example, are used in display as much as in actual combat, with rivals assessing each other's antler size and configuration before deciding whether to engage in a potentially dangerous physical confrontation. The elaborate crests of many bird species serve similar functions, advertising genetic quality to potential mates without requiring the risk and energy cost of direct physical competition. If the horns of Carnotaurus function similarly, they may have allowed individuals to recognize each other as members of the same species across distance, may have permitted males to assess each other's relative fighting ability without direct combat, and may have played a role in mate attraction if larger, more symmetrical, or more brightly colored horns were preferred by potential mates. The intraspecific combat hypothesis is closely related to the display hypothesis and is in many ways its natural extension. Display, in the animal world, often grades into actual physical competition when the display signals are insufficiently decisive. Male deer that cannot determine relative dominance through antler display will engage in antler-locking combat. Male bison that cannot assess each other through posture and vocalization will charge and clash heads. If Carnotaurus engaged in similar head-to-head or horn-to-horn competition with rivals of its own species, the horns would have provided both a weapon for delivering impact and a target for receiving impact in a way that concentrated force on the strengthened bony structures of the skull rather than on the more vulnerable tissues of the face and neck. The deep, robust nature of the Carnotaurus skull, which is not built like the lightweight, open-structured skulls of many large predators, but is instead reinforced and thickened in ways that suggest it was designed to absorb force, is consistent with a lifestyle that included head impact competition. The prey capture hypothesis is more controversial and requires more specific anatomical evidence to support. The idea that the horns might have been used to stun, pin, or control prey during a hunt is intuitively appealing, but is not strongly supported by the biomechanics of the skull and neck as currently understood. A horn-first charge into a large titanosaur would have subjected the Carnotaurus skull to extraordinary forces. And while the skull was robust, there is a reasonable question of whether it was reinforced in the specific ways that would have been required for repeated high-force contacts with large prey animals. Most researchers currently favor the display and intraspecific competition explanations over the prey capture explanation, though this is a question that new evidence could revise at any time. Beyond the horns, the skull of Carnotaurus reveals several other features of anatomical significance that tell us important things about how this animal sensed its world, how it killed its prey, and how it compared to other large predators of its time. The eye sockets were large and faced laterally to a significant degree, suggesting a wide field of view that would have been useful for scanning an open landscape for both prey and threats. The brain cavity, which can be partially reconstructed from the internal dimensions of the skull, suggests a brain that was reasonably well developed for a non-avian dinosaur, with features consistent with good olfactory processing, suggesting that smell was an important sense for this animal, as it is for most large predators. The teeth of Carnotaurus were relatively slender and blade-like compared to those of tyrannosaurs, suited more for slicing and cutting through flesh than for crushing bone. This is consistent with a predation style that involved quick, devastating bites to vulnerable areas of prey, rather than the sustained bone crushing that tyrannosaurs could deliver, and it has implications for how Carnotaurus interacted with its prey after the initial attack. A predator with blade-like slicing teeth would have targeted soft tissues, aiming for the neck, the abdomen, the flanks, seeking the quick loss of blood and the rapid incapacitation of prey, rather than the grinding, prolonged battle of attrition that a bone crusher could sustain. The lower jaw of Carnotaurus was correspondingly deep and strong, providing the muscular anchor points for powerful jaw-closing muscles that could drive those slicing teeth through flesh with force. Studies of the skull mechanics of Carnotaurus, using computer modeling to simulate the stress distributions during biting, have suggested that while the bite force of Carnotaurus was not as extreme as that of Tyrannosaurus rex, it was well adapted for the specific kind of predation that this animal's ecology and body plan required. The mechanics of the skull suggest a predator that could deliver fast, forceful bites to specific target areas of a prey animal, biting and withdrawing rather than locking onto prey and sustaining contact. A hunting strategy more consistent with what we see in large felids like lions than with what we see in the grip and crush approach of the Tyrannosaurs. The neck of Carnotaurus was thick and muscular, an observation supported not just by the size and orientation of the vertebrae, but by the presence of attachment scars on the bones that indicate very large neck muscles. This powerful neck musculature was not just for supporting the relatively heavy skull, but may have been part of the predatory weaponry, allowing the animal to deliver powerful strikes with the head in a lateral sweeping motion that could knock prey off balance or drive the teeth deeply into flesh in a single explosive movement. Some researchers have compared this hypothetical strike behavior to the lateral striking attacks of large crocodilians, which can deliver devastating bites by swinging the head sideways with the full power of the neck and body muscles behind it. If Carnotaurus hunted in a similar way, leading with sideways head strikes rather than the forward lunge of most theropods, the deep, robust skull and the powerful neck muscles would both make sense as adaptations for this specific technique. And then there are the arms. The arms of Carnotaurus are, after the horns, perhaps the most immediately striking feature of the animal. And in some ways, they are the more scientifically interesting of the two, because they raise questions that go to the heart of how we understand the relationship between body form and function in extinct animals. The forelimbs of Carnotaurus were tiny, not merely small in the way that the forelimbs of all abelosaurids were smaller than those of other large theropods, but genuinely, astonishingly tiny, even by abelosaurid standards. The upper arm bone, the humerus, was robust and fairly standard in its overall dimensions, but the bones of the forearm, the radius and ulna, were dramatically shortened, and the hand, if it can even be called that, was reduced to a cluster of stubby, largely immobile elements that bore 4 poorly differentiated fingers without the ability to grasp or manipulate in any meaningful way. The forelimbs of Carnotaurus were not useful for catching prey. They were not useful for manipulating objects of any kind. They were not useful for balance or for pushing the animal upright from a resting position on the ground. They were, to be completely blunt about it, not obviously useful for anything that a predator needs to do. And this raises a question that is genuinely profound when you sit with it. Why did Carnotaurus have them at all? Why did evolution not simply eliminate these structures entirely, rather than leaving this vestigial remnant of what had once, in the distant ancestors of this lineage, been functional predatory appendages? The answer to this question touches on one of the most important and fascinating principles of evolutionary biology, the principle of evolutionary constraint. Natural selection is extraordinarily powerful, but it does not operate on a blank canvas. It operates on whatever biological material already exists, modifying it incrementally, generation by generation, and it can only move in directions that each individual modification, each single generation's change, provides some advantage over the previous generation. When a structure is not positively harmful to the organism, when it costs relatively little to maintain and does not significantly reduce survival or reproduction, natural selection may have very little pressure to eliminate it. The forelimbs of Carnotaurus were metabolically inexpensive, requiring relatively little energy to develop and maintain given their tiny size. They were not getting in the way of the animal's locomotion or its hunting, and so there was no strong selective pressure to remove them entirely, even though they served no obvious function. They persisted as evolutionary relics, vestiges of a more arm-bearing past, carried forward into an animal that had no use for them, but no compelling reason to be rid of them. This is a story that repeats itself throughout the history of life. The human body carries vestigial structures, including the coccyx, which is the remnant of a tail that our ancestors possessed, the erector pili muscles that cause goosebumps and were far more useful when our ancestors had more body hair, and the plantaris muscle in the leg that is so underdeveloped in modern humans that it is absent in roughly 10% of people. All of these are evolutionary relics, maintained not because they are particularly useful, but because eliminating them entirely would require a series of specific mutations that have simply not arisen or been selected for. Carnotaurus was carrying similar relics on its sides, four-fingered remnants of a predatory heritage that this particular lineage had moved far beyond. The skin of Carnotaurus is something that we can speak about with unusual confidence for a large predatory dinosaur, because the original Argentinian specimen preserved not just bones, but skin impressions. Fossilized traces of the actual surface texture of the animal's hide, pressed into the surrounding rock during the process of fossilization in a way that preserved the pattern with remarkable detail. These skin impressions are among the most valuable aspects of the entire specimen because they give us information that bone alone cannot provide. Information about the external appearance of the living animal, about the texture and pattern of its integument, and about whether it bore any elaborate surface structures beyond the horns and the basic bone architecture of the skeleton. What the skin impressions of Carnotaurus reveal is a covering of small, non-overlapping scales arranged in a pattern of small, rounded tubercles, interspersed with occasional larger, rounder, more boss-like scales. There are no feathers. There are no elaborate frills or crests of soft tissue beyond what the bone itself suggests. The skin was essentially a tough, textured, pebbly hide, not unlike the skin of a modern monitor lizard or a large crocodilian, functional and understated in a way that contrasts with the dramatic bony ornamentation of the skull. This skin evidence has been important in the broader scientific conversation about feathers in theropod dinosaurs, because while many theropods are now known or inferred to have had feathers or feather-like structures, The skin impressions of Carnotaurus suggest that at least some large abelisaurids had reverted to, or simply retained, a fully scaled integument without any fibrous or feathery covering. The coloration of Carnotaurus in life, like the coloration of all non-avian dinosaurs, is a question that the fossil record cannot directly answer. No pigment survives in the fossilized skin of Carnotaurus. No melanosomes, the cellular structures that carry pigment information and that have been recovered from some feathered dinosaur specimens, have been found in the Carnotaurus skin impressions. We must therefore reason about color indirectly through the biology and ecology of the animal, through what we know about the coloration patterns of modern large predators, and through an honest acknowledgement of how much we simply do not know. Modern large predators tend toward earth tones and patterns that provide camouflage against their hunting environments. Lions are tawny gold to match the dry grasslands they hunt in. Tigers are orange with black stripes that break up their outline in the dappled light of forest edges. Crocodilians are dark olive green and brown, matching the murky water and muddy banks they inhabit. If Carnotaurus was primarily a predator of open or semi-open floodplain environments, hunting large sauropods across broad, relatively unobstructed terrain, camouflage may have been less important than in a forest-dwelling ambush predator, and the coloration may have been relatively uniform and muted. But if Carnotaurus used ambush tactics, approaching prey under cover of vegetation before launching a high-speed attack, then more elaborate camouflage patterns would have been advantageous, and more elaborate coloration is possible. Some paleo artists have imagined Carnotaurus with vivid coloration on the horns or around the eye region, perhaps involving bright reds or yellows or iridescent blues, using those structures as display signals in the way that many modern animals use brightly colored facial features for species recognition and mate attraction. This is biologically plausible, since the horns were almost certainly used in display and bright coloration would have enhanced their visibility and communicative effectiveness. But it remains speculation, one possible truth among many possible truths. And the honest narrator must hold it lightly, offering it as a possibility worth imagining rather than a fact worth asserting. Let the picture settle for a moment. The textured hide, the deep, blunt skull, the horns projecting above the eyes, the tiny, useless arms folded against the sides of a powerfully muscled body, the long, strong tail balancing everything behind. This was Carnotaurus. This is what walked the floodplains of Patagonia 70 million years ago. And the fact that we know it as well as we do is itself a remarkable story. The story of a discovery that transformed our understanding of what a predatory dinosaur could be. The discovery of Carnotaurus is a story that deserves its own unhurried telling, because it is one of those moments in the history of science where a single find, a single set of bones in a particular hillside, opened a window onto a world that had been completely invisible to human knowledge until that precise moment. Before 1984, the abelisauride family of dinosaurs was almost entirely unknown. After 1984, after the excavation of the Carnotaurus specimen from the Chorrillo Formation in the Chubut province of Argentina, the entire picture of large predatory dinosaurs in the southern hemisphere had to be reimagined from the ground up. The man responsible for this transformation was José Fernando Bonaparte, an Argentinian paleontologist who spent the better part of his career making discoveries of exactly this magnitude. Bonaparte was not a scientist who found his work at the edge of what was already known. He was the kind of scientist who kept finding the entirely unknown, who kept reaching into rocks and pulling out animals that nobody had imagined existed. His career is studded with extraordinary discoveries, and Carnotaurus is perhaps the most spectacular of them all, not just because of the animal itself, but because of the condition of the specimen he found and what that condition made possible. The Carnotaurus specimen was found on land belonging to a rancher named Angel Sastre, in a remote region of Patagonia where the wind is almost constant, and the landscape is the particular kind of barren that becomes beautiful once you understand that beneath the dusty surface lies a history of incomprehensible depth. The bones were discovered eroding from a hillside, as fossil bones so often are, exposed by the slow, patient work of wind and rain, removing the rock that had encased them for the better part of 70 million years. Bonaparte's team recognized the significance of what they were seeing quickly, and the excavation that followed was meticulous, careful, and ultimately transformative. What made the Carnotaurus specimen so extraordinary was not merely its existence, but its completeness. Large predatory dinosaurs are frequently known from fragmentary material, a few bones here, a partial skull there, isolated teeth scattered across a formation. The Carnotaurus specimen was, by the standards of large theropod paleontology, remarkably complete. The skull was nearly intact and beautifully preserved, allowing the horns and the deep, blunt profile and the eye sockets and the jaw mechanics to be studied with a degree of confidence that fragmentary material never allows. Much of the postcranial skeleton was present as well, giving researchers access to the forelimbs, the hindlimbs, the vertebral column, and the overall proportions of the animal. And then there were the skin impressions, those extraordinary traces of the actual surface of the living animal pressed into the rock during decomposition, which elevated the specimen from the extraordinary to the truly unique. Bonaparte described the animal formally in 1985, the year after the excavation, in a scientific paper that sent a wave of quiet astonishment through the paleontological community. Here was a large predatory dinosaur from South America with bull-like horns on its head, vestigial forelimbs of startling uselessness, and preserved skin. Here was evidence that the isolated evolutionary experiment of South America had been running far stranger and far more creative experiments than anyone had suspected. And here was, in the quality and completeness of the preserved material, a window into late Cretaceous South America that was clearer and more detailed than anything previously available. The years after the initial description saw the specimen prepared with increasing care and studied with increasing sophistication as new analytical methods became available. The skin impressions were examined in detail and found to be consistent across most of the body surface, suggesting that the textured, tuberculated hide was a general feature of the animal rather than a localized variation. The skull was subjected to various analyses, including computer tomographic scanning in later years, allowing the internal structure of the skull, including the brain cavity and the paths of the cranial nerves and blood vessels, to be examined without the destructive cutting that was the only alternative in earlier decades. The phylogenetic analysis of Carnotaurus, the determination of its exact evolutionary relationships within the broader family of Abelosaurids, and within the still larger context of theropod dinosaur evolution, has been a long and ongoing process that has produced increasingly detailed and increasingly confident results as more Abelosaurid species have been found and described from South America, Africa, Madagascar, India, and possibly Europe. The Abelosaurid family, it has become clear, was a genuinely global radiation of large predatory dinosaurs that occupied the role of apex predator across much of the Gondwanan landmasses during the Cretaceous, the same ecological role that the tyrannosaurs filled in the Northern Hemisphere. This realization has been one of the most important insights to emerge from the Carnotaurus discovery and the subsequent flowering of abelosaurid paleontology that it helped inspire. Gondwana, the supercontinent that had once united South America, Africa, Antarctica, India, Madagascar, and Australia, had been breaking up throughout the Mesozoic era, its component landmasses drifting apart on the slow currents of plate tectonics. By the Late Cretaceous, these landmasses were substantially separated, connected at best by periodic land bridges and shallow seaways that allowed some faunal interchange, but maintained a fundamental biogeographic distinctiveness between them. Yet the abelosaurids were found on multiple Gondwanan landmasses, in various stages of the separation, suggesting that their common ancestor had lived on an earlier, less fragmented Gondwana, and that as the landmass broke apart, different abelosaurid lineages had been carried on the separating fragments, evolving in isolation into the diverse species that paleontologists are now discovering across the Southern Hemisphere. To rest in this knowledge for a moment, this knowledge that the world was once arranged so differently that what is now multiple separate continents was once a single vast landmass, that the animals of Argentina and Madagascar and India and Africa were once parts of the same connected biological community, is to feel something of the vertiginous depth of geological time and the extraordinary creativity of biological evolution. The Carnotaurus that walked Patagonia was distantly related to the abelosaurids of the Deccan Plateau in India, to the strange and wonderful Majungasaurus of Madagascar, to the ceratosaurs of Tanzania in Africa. They were cousins separated by the slow drift of continents, carrying the family resemblance of a shared ancestor in their blunt skulls and reduced arms and elaborated head ornamentation, and diverging in the precise expression of those features as their separate evolutionary paths unfolded over millions of years. Now let us return to the living animal, return to the floodplain, to the warm Patagonian day, to the long view of river and vegetation and distant hills that would have been the daily visual landscape of a Carnotaurus moving across its territory. And let us think carefully about how this animal moved, because the locomotion of Carnotaurus is one of the most fascinating and most scientifically contentious aspects of its biology, with implications that go far beyond the simple question of how fast it could run. The locomotor capabilities of Carnotaurus have been studied in considerable detail by researchers using methods that would have been completely unavailable to Bonaparte when he first described the animal. Modern biomechanical analysis uses computer modeling of the skeleton, estimates of muscle mass based on the size and orientation of attachment scars on the bones, and mathematical modeling of the forces and movements involved in locomotion to produce quantitative estimates of the speed and gait capabilities of extinct animals. These methods are not perfect. They involve assumptions about soft tissue that cannot be directly measured from fossils, and simplifications of complex biological systems that inevitably introduce some degree of uncertainty. But they have produced results for Carnotaurus that are genuinely remarkable, and that have significantly influenced how researchers think about this animal's ecology and predation strategies. The key study in this regard was published in 2016 by a team led by Ruber Molina Perez and Asier Laramendi, building on earlier work by multiple researchers, and it suggested that Carnotaurus was among the fastest large theropod dinosaurs known from the Mesozoic, potentially capable of reaching speeds of around 56 kilometers per hour in short bursts, with a sustained running speed that was likely in the range of 45 kilometers per hour. To put these numbers in perspective, a top human sprinter can reach approximately 44 kilometers per hour for a very short distance. Carnotaurus, at roughly 8 meters in length and perhaps 1 to 1.5 metric tons in mass, may have been capable of outrunning a human being over short distances. Not comfortably, not with the ease that a cheetah outpaces a gazelle, but with a speed that would have been extraordinary for an animal of its size and mass. How was this speed achieved? The answer lies in the proportions of the hind limbs and in the particular configuration of the tail musculature that studies of the Carnotaurus skeleton have revealed. The hind limbs of Carnotaurus were long relative to body size, with a femur, the thigh bone, that was proportionally shorter relative to the lower leg than in many comparable theropods, creating a limb configuration that is associated with faster running speeds in the mathematical models of dinosaur locomotion. Longer lower limbs relative to upper limbs are a feature of fast runners across the history of vertebrate life, from the long-legged ostriches among birds to the slim-legged cheetahs among mammals, and the leg proportions of Carnotaurus slot it into the faster end of the large theropod spectrum. But the limb proportions alone do not account for the speed estimates. There is also the matter of the tail, and specifically the tail muscles, which play a role in locomotion that is sometimes overlooked in popular accounts of dinosaur biology, but that has become increasingly recognized as central to understanding how large theropods moved. The tail of a bipedal dinosaur was not simply a counterweight or a balancing organ, though it served those functions as well. It was the anchor point for a set of muscles, primarily the caudofemoralis muscles, that ran from the tail vertebrae forward to attach on the upper part of the femur. When these muscles contracted, they pulled the femur backward, driving the leg into the power stroke of each step. In animals with large muscular tails, these caudofemoralis muscles are large and powerful, contributing substantially to the total locomotor force. The tail of Carnotaurus, while not preserved in complete detail in the original specimen, appears from the bones that are preserved to have been well muscled and relatively stiff in the distal portion, with a particular arrangement of the tail vertebrae and their associated processes that suggests a tail capable of generating significant caudofemoralis force while also being less flexible laterally than the tails of many other large theropods. This stiffened tail configuration is associated in modern models with more efficient, straighter line running rather than the more flexible tail use of animals that turn frequently, and it fits with the picture of Carnotaurus as a cursorial predator, a fast runner capable of sustained pursuit of prey across open ground, rather than the ambush specialist of dense forest environments. The picture that emerges from this biomechanical analysis is of a predator that was genuinely unusual among large theropods, not the plodding, ambush-dependent hunter of popular imagination, but an animal capable of active, sustained pursuit of prey across the open floodplains and savannas of Cretaceous Patagonia. This has significant implications for how we understand the hunting behavior of Carnotaurus and its relationships with the titanosaur prey animals that shared its world. Hunting large sauropods is, as we noted earlier, not a simple proposition. The titanosaurs of late Cretaceous South America were among the largest animals that have ever walked on land, and even the juveniles and subadults that a predator of Carnotaurus's size could realistically target were substantial animals capable of inflicting serious harm through defensive kicks, tail sweeps, and the sheer mechanical effect of their enormous mass. A predator that can achieve high speed has a significant advantage in this context because speed creates options that slower predators do not have. A fast predator can catch prey before it reaches the protective core of a herd. It can pursue a separated or injured individual across open ground. It can break off an unsuccessful attack and reposition for another approach more quickly than a slow predator. And it can escape from a failed attack before the prey animal's defensive responses can connect, reducing the risk of injury that is an ever-present hazard for large predators that hunt prey many times their own mass. The hunting strategy that the anatomy of Carnotaurus most strongly suggests is what some researchers have described as a pursuit-predation strategy, an approach in which the predator uses its speed advantage to catch and bring down prey through sustained or repeated high-speed charges, rather than through the ambush and grapple approach of slower, more powerfully armed predators. In this strategy, the target would typically be an isolated individual, separated from the protective mass of a herd or a young, old, or otherwise compromised animal whose speed and defensive capability were below the herd's average. The Carnotaurus would have approached at speed, closing the distance before the prey animal could react effectively, and then delivered a series of rapid, forceful bites to vulnerable areas of the prey's body, targeting the neck, the flanks, or the base of the tail, before withdrawing and allowing the prey to weaken from blood loss and exhaustion. This is, in its broad outlines, the hunting strategy of many large felids today, particularly the big cats that hunt in open environments. Lions hunting wildebeest, cheetahs hunting gazelles, leopards hunting impala, all use versions of this approach. Identify a vulnerable target, use speed or stealth to close the distance, deliver incapacitating bites to the throat or neck, and let the prey weaken and die, rather than engaging in a prolonged and dangerous struggle. The anatomy of Carnotaurus, with its running adapted limbs, its powerful neck musculature, its slicing teeth, and its compact skull designed perhaps to deliver powerful lateral strikes, is consistent with a predatory style that was in many ways more like a large cat than like the bone-crushing tyrannosaurs to which popular culture most often compares it. The question of whether Carnotaurus hunted alone or in groups is one that the fossil record cannot definitively answer. Modern large predators show a wide spectrum of social hunting behavior, from the strictly solitary snow leopard and polar bear to the cooperative pride hunting of lions and the pack hunting of wolves and African wild dogs. The evidence for or against social hunting in any extinct predator requires either finding multiple individuals together in a context that suggests coordinated behavior, such as a single prey carcass surrounded by multiple predator individuals, or finding other behavioral evidence preserved in trace fossils or through reasoning from the animal's likely ecological context. For Carnotaurus, such evidence is not available in the single known specimen, and the question must remain open. The ecological logic of group hunting in a predator that targeted large, well-defended prey like titanosaur sauropods is compelling. A group of Carnotaurus individuals working together could have coordinated attacks from multiple angles, distracting defensive adults while smaller or more vulnerable members of a sauropod herd were targeted, dividing the prey's defensive responses and reducing the risk of injury to any individual attacker. But cooperation requires cognitive complexity, the ability to recognize and respond to the behavior of conspecifics in a coordinated way. And while the brain of Carnotaurus was certainly adequate for the demands of individual predation in a complex environment, whether it extended to the kind of sophisticated social coordination that effective pack hunting requires, is something we cannot determine from the fossil evidence currently available. What we can with some confidence is that Carnotaurus was almost certainly territorial, as most large predators are. The horns, whatever else they were for, are strongly suggestive of an animal for which individual identity and competitive display mattered. An animal for whom other members of its own species were potential rivals as much as potential mates, and in which the visual and possibly physical signaling of status and capacity was important enough to justify the investment of biological resources in growing and maintaining those prominent cranial ornaments. A territorial large predator, in a world of limited prey resources, would have maintained and defended a home range large enough to supply it with adequate food, would have been alert to the presence of rivals, and would have used display and, when necessary, direct combat to maintain access to that territory and its resources. The combat between rival Carnotaurus individuals, if it occurred, was probably centered on the horns in the same way that combat between rival bovids is centered on their horns. Head-to-head engagement, perhaps combined with lateral shoving and body-to-body pushing, would have allowed rivals to assess each other's strength and determination without necessarily inflicting lethal injuries. Providing the information needed to establish dominance hierarchies or territorial boundaries without the cost of serious combat that could leave both animals injured and vulnerable. The reinforced nature of the Carnotaurus skull, with its thickened bones and robust overall architecture, is consistent with an animal that was built to absorb the impacts of such head-to-head encounters without suffering structural damage. Picture two Carnotaurus individuals facing each other on a broad, sun-warmed floodplain, the grass of the Late Cretaceous flattened around their feet, the distant river a silver thread on the horizon. Their horns catch the afternoon light. Their bodies are held rigid and upright, every muscle communicating tension and readiness. They circle each other slowly, each reading the other's size and condition and posture with the practiced assessment of animals that have been doing this for their entire lives. The encounter may end in one retreating without contact. It may end in a brief, explosive exchange of horn strikes that leaves both shaken but uninjured. Whatever happens, it is a performance of biological identity, a statement in the language of bodies and horns and territorial claim that has been written and rewritten on the floodplains of Patagonia for millions of years. Let that image rest in your mind for a while, two bull-horned predators in the gold light of a Cretaceous afternoon, and let yourself rest with it. Let the warmth of the imagined sun settle over you as the story continues its slow, unhurried way through the extraordinary life of this extraordinary animal. The world that Carnotaurus inhabited was not just a backdrop against which its life played out. It was an active, shaping force, an environment that pressed its particular demands against the biology of every organism within it, and rewarded those biological innovations that best met those demands. To understand Carnotaurus fully, we must spend some real time with the late Cretaceous Patagonian world, with its climate and its seasons and its plant communities and its other animals, because it was that world, in all its specific detail, that selected for the bullhorns and the vestigial arms and the running legs and the deep blunt skull. Evolution does not produce abstract perfection. It produces local solutions to local problems. And the local problems of late Cretaceous Patagonia were very specific indeed. The climate of Patagonia in the late Cretaceous was significantly warmer and more humid than today. The global temperature was elevated relative to the present world, with higher concentrations of carbon dioxide in the atmosphere, maintaining a greenhouse effect that kept the planet warmer and more uniformly temperate from pole to pole. There were no permanent polar ice caps. The temperature gradient from the equator to the poles was less steep than today, meaning that the high southern latitudes where Patagonia sits were dramatically warmer relative to modern conditions. The sea level was higher, with shallow seas flooding the interiors of many continental landmasses, and the continental configuration was somewhat different from today, though recognizable. In this warmer world, Patagonia would have experienced a climate perhaps more like what we see today in parts of northern Argentina or southern Brazil. Relatively warm year-round, with a pronounced wet season when the rivers flooded their banks and the floodplains were inundated with shallow water, followed by a drier season when the rivers retreated to their channels and the vegetation on the plains dried and thinned. This seasonality, while less extreme than the cold winters of modern Patagonia, would still have imposed a rhythm on the lives of all the animals in the ecosystem, a rhythm of abundance and scarcity, of wet and dry, of easy feeding and harder times that shaped behavior and physiology and migration patterns in ways we can partially reconstruct from the geological and paleontological record. The plant communities of Late Cretaceous Patagonia were dominated by the new evolutionary arrivals that were transforming the world's vegetation during the Cretaceous period. The angiosperms, the flowering plants. The angiosperms had originated earlier in the Cretaceous, probably in the early Cretaceous, somewhere around 130 to 140 million years ago. And by the late Cretaceous, they had diversified enormously and spread across most of the world's land surfaces, beginning to displace the gymnosperms, the cone-bearing plants like conifers and cycads and ginkgos that had dominated terrestrial vegetation for the preceding 100 million years. The Patagonian flora of the late Cretaceous included both early angiosperms, probably relatively low-growing shrubs and ground cover plants in many cases, and a continued diversity of gymnosperms in the form of various conifers and ferns that maintained their presence in the ecosystem alongside the flowering plant newcomers. This vegetation provided the food base for the Titanosaur sauropods that were the dominant large herbivores of the ecosystem, and the Titanosaurs in turn provided the primary food resource for Carnotaurus and the other large predators of the Chirillo Formation fauna. The Titanosaurs were extraordinarily diverse in late Cretaceous South America, with numerous genera and species representing a range of body sizes from the relatively modest to the truly gigantic. The Titanosaur community of Patagonia in the late Cretaceous was not a monoculture of similar animals, but a diverse assemblage of related species that partitioned the available vegetation resources through differences in feeding height, preferred food plants, and habitat use, much as the different species of large herbivores in modern Africa partition the savanna vegetation between them. This diversity of prey would have meant that Carnotaurus had options. Not just one type of prey animal, but a spectrum of possible targets, ranging from medium-sized titanosaurs of perhaps 10 to 20 metric tons, which would have been challenging but theoretically manageable for a predator of Carnotaurus's size and speed, down to juveniles and subadults of even the largest species, which, though potentially large in absolute terms, were not yet the immovable, invulnerable giants that the adult titanosaurs of the largest species represented. A young Patagotitan, for example, might have reached a body mass of several tons before it was genuinely beyond the reach of a large Carnotaurus, and during the years of its growth from hatchling to that threshold, it would have been a potential prey item for an opportunistic predator that could match it in speed and outmatch it in predatory capability. The relationship between predator and prey in a complex ecosystem like Late Cretaceous Patagonia was not a simple one-to-one pairing, but a web of interactions in which multiple predator species competed for access to multiple prey species, and in which the prey species exerted their own evolutionary pressure on the predators through their defensive adaptations and their behavioral responses to predation risk. The titanosaurs were not passive victims. They were large, powerful animals with their own suite of anti-predator adaptations, including the bony osteoderms that some species carried in their skin, the powerful tails that could deliver devastating blows to an attacking predator, and the herding behavior that concentrated protective adults around the most vulnerable young animals. Some titanosaur species also appear to have had the ability to actively mob or chase away predators, a behavior seen in modern large herbivores like elephants and hippos, where the sheer mass and collective aggression of a group of large animals can deter even the most formidable predator from attacking. If the titanosaurs of Late Cretaceous Patagonia engaged in similar group defensive behavior, then a Carnotaurus approaching a large, intact herd would have faced not just the defensive capabilities of any individual animal, but the collective threat of a group that might actively pursue and injure the predator. This predation pressure from prey would have reinforced the selection for speed in Carnotaurus, since a predator fast enough to withdraw quickly after a failed attack would avoid the consequences of mob defense more effectively than a slower predator caught within range of multiple angry titanosaurs. The other predators that shared the Late Cretaceous Patagonian ecosystem with Carnotaurus add further complexity to the picture of its ecological context. While Carnotaurus was undoubtedly the apex predator of its ecosystem, the largest and most formidable carnivore on the landscape, it was not the only large carnivore. Various abelosaurid relatives, somewhat smaller in body size, occupied related but potentially distinct ecological niches, taking prey of different sizes or using different hunting techniques in different microhabitats. Smaller theropods, including various non-abelosaurid forms, occupied the ecological space of medium-sized predators, taking prey that was too small to attract the attention of a Carnotaurus, but that provided an important food resource in their own right. There were also the flying predators, the pterosaurs, whose diversity and abundance in the Late Cretaceous is sometimes underappreciated in popular accounts of Mesozoic life. Some Late Cretaceous pterosaurs were genuinely enormous animals, with wingspans exceeding 10 meters in the case of forms like Quetzalcoatlus, and even the largest of these flying reptiles may have been capable of taking prey of considerable size during terrestrial foraging. Whether the pterosaurs of Late Cretaceous Patagonia competed directly with Carnotaurus for food resources is uncertain, but their presence in the ecosystem added yet another dimension to the complex web of predatory relationships within which Carnotaurus existed. And in the rivers and lakes and coastal wetlands that bordered the floodplains, there were large crocodilians, ancient relatives of the crocodiles and alligators of today, that occupied the aquatic and semi-aquatic predator roles that no dinosaur with its fully terrestrial body plan could fill. These crocodilians, some of which reached considerable sizes, would have been important components of the fauna, taking terrestrial animals that came to the water's edge to drink, hunting the fish and turtles and other aquatic animals of the river systems, and potentially competing with terrestrial predators like Carnotaurus for access to carcasses near water. The scavenging relationships in this ecosystem also deserve consideration. Modern large predator communities are sustained not only by active hunting, but also by the consumption of carrion and the ability to locate and access carcasses before other scavengers consumes the resource is an important aspect of predator ecology. Carnotaurus, with its well-developed olfactory system, would have been capable of detecting decomposing carcasses at considerable distance, and the speed that made it effective as a pursuit predator would also have allowed it to reach carcasses quickly and to dominate them against smaller or slower competitors. The relationship between active predation and scavenging in the feeding ecology of Carnotaurus is impossible to determine precisely from the fossil record, but both were almost certainly components of a flexible feeding strategy that took advantage of whatever food sources were available in a seasonally variable environment. This brings us to one of the more philosophical aspects of thinking about the life of Carnotaurus and creatures like it. We have a tendency, when imagining ancient predators, to think of them primarily as hunters, as active and dramatic agents pursuing and killing their prey in the vivid way that nature documentaries capture on film. And this is a real and important part of what they were. But it is only part. The daily reality of being a large predator in any ecosystem, ancient or modern, involves far more time spent resting, patrolling territory, interacting with conspecifics, drinking, sheltering from weather, and simply existing in a state of quiet alertness than it does active hunting and killing. Lions in Africa spend roughly 20 hours of every day resting. Tigers rest almost as much. The dramatic hunts that define these animals in the human imagination occupy a tiny fraction of their actual lives. Carnotaurus, by this logic, spent most of its time not hunting. It spent most of its time in whatever state of rest and watchful patience corresponds to the experience of a large Cretaceous predator, lying in the shade of a conifer or a tree fern, its muscular tail stretched out behind it, its horned head lowered and relaxed, breathing slowly in the warm afternoon while the titanosaurs moved at a safe distance across the floodplain and the pterosaurs circled in thermals overhead. It spent time at the river, drinking carefully in the manner of large predators that are never entirely off guard even at the water's edge. It spent time moving through its territory, maintaining awareness of what was happening within the boundaries of the range it defended, noting the presence of rivals or potential mates, and responding appropriately to each. In this patient, slow, mostly quiet life, punctuated by the explosive violence of occasional hunts and the lower-key tension of territorial encounters, Carnotaurus was simply being alive in the way that all large organisms are alive. Mostly gentle, and most of the time simply present in their world. This is worth sitting with for a moment. The image of Carnotaurus as a thundering engine of destruction is real but partial. The other image, of a large predator resting in the heat of the day with its eyes half closed, is equally real, equally part of what it meant to be this animal in this world, and in some ways more restful to contemplate as the day winds down and sleep draws near. The senses of Carnotaurus provide another window into how this animal experienced its world. We have touched on olfaction already, but it deserves more extended consideration. The sense of smell in large predatory dinosaurs is inferred primarily from the relative size and complexity of the olfactory regions of the brain, which can be partially reconstructed from the internal dimensions of the skull cavity and from the size of the nasal passages that delivered air to the olfactory epithelium. In Carnotaurus, the evidence suggests a reasonably well-developed olfactory system not as extreme as that of some other large theropods, but adequate for detecting prey and conspecifics at distances of several hundred meters under favorable wind conditions. The hearing of Carnotaurus, similarly inferred from the dimensions of the inner ear structures visible in the skull, appears to have been sensitive to a range of frequencies relevant to detecting the movements of large animals and to communication between individuals of the same species. Low-frequency sounds carry particularly well over long distances in open environments, and a predator of large prey animals in open terrain would have benefited from sensitivity to the low rumbles and ground vibrations produced by the movement of large herds of titanosaurs. There is even speculation, though it is speculative in the truest sense, that Carnotaurus may have been capable of producing low-frequency vocalizations of its own, used in territorial signaling and mate attraction in the way that modern crocodilians use their deep bellowing calls. The vision of Carnotaurus presents an interesting case that is somewhat different from what is typically described for large theropod predators. The eye sockets of Carnotaurus face somewhat to the sides rather than directly forward, suggesting that the visual fields of the two eyes overlapped less than in some other large theropods, and that binocular vision, the depth perception that forward-facing eyes provide, was not as pronounced as in animals with more frontally directed eyes. This seems initially puzzling for a pursuit predator, because depth perception is valuable for judging distances during high-speed chases and attacks. However, the wide lateral field of view provided by more laterally placed eyes has its own advantages, particularly in an open environment where detecting threats and opportunities over a wide angle is more important than precise depth perception at close range. One possibility that has been discussed is that the position of the horns themselves may have influenced the evolution of eye placement in Carnotaurus. The horns project above and forward of the eyes, and if the eyes faced directly forward, the horns would have partially obstructed the visual field. By placing the eyes somewhat more laterally, the visual obstruction created by the horns is reduced, and the animal can maintain a wide field of view around the visual intrusion of its own cranial ornamentation. This is a form of evolutionary compromise, a solution to the geometrical problem of carrying large display structures on the head without completely blocking vision. And it is an example of the kind of integrated, whole-body evolutionary logic that makes studying extinct animals so consistently surprising and rewarding. The growth of Carnotaurus from hatchling to adult was a journey that has been partially reconstructed from the evidence of bone microstructure in specimens of different sizes, combined with the general understanding of abelosaurid growth patterns that has been developed from studies of multiple species within the family. Like all dinosaurs, Carnotaurus grew rapidly in youth, laying down bone tissue at rates that are more comparable to modern birds and mammals than to modern reptiles, in a pattern that reflects the elevated metabolic rates that the bone histological evidence consistently indicates for non-avian dinosaurs generally. A hatchling Carnotaurus would have emerged from an egg relatively small, probably less than half a meter in length, already equipped with the basic body plan of the adult, but with proportions that were somewhat different. The head and eyes proportionally larger relative to body size, as is typical of the young of most vertebrates, and the horns either absent or present, only as small bony bumps that would have given no hint of the impressive structures they would eventually become. Growth would have been rapid in the early years, with the young Carnotaurus adding substantial body mass each year. and it would have reached something approaching adult size within roughly a decade, though continued, slower growth for years after reaching reproductive maturity is likely. During the vulnerable years of growth from hatchling to subadult, young Carnotaurus faced predation risks from other predators in their ecosystem. Adults of their own species may occasionally have been threats, since cannibalism in large predators is not unusual and is documented in various modern species. Other large theropod predators in the ecosystem would have been potential threats to young animals of any species, including young Carnotaurus. And the larger crocodilians of the river systems would have been genuine dangers to any animal small enough to be taken at the water's edge. The transition from vulnerable juvenile to capable adult was a gauntlet through which only a small fraction of individuals would have passed, with the mortality rate in the first years of life being the highest of any stage of the lifespan. Those individuals that survived to adulthood, that passed through the dangerous years of growth to reach the size and capability of a fully developed Carnotaurus, would have been animals of genuine physical power and ecological dominance. An adult Carnotaurus in its prime, healthy, well-fed, in possession of a productive territory, was essentially invulnerable to predation, the unchallenged master of its portion of the Patagonian floodplain, limited in its ecological impact only by the availability of prey and the competition of other adults of its own kind for access to that prey. In such a position, the life of an adult Carnotaurus would have had a rhythm of confident competence, a daily routine of territorial patrol and opportunistic feeding and seasonal reproduction that could have continued for decades. The maximum lifespan of Carnotaurus is not known with precision, but studies of bone microstructure in abelisaurids and other large theropods suggest that these animals could potentially live for several decades, with some estimates suggesting maximum lifespans of 40 or more years for the largest individuals. Over such a lifespan, a successful Carnotaurus would have participated in many breeding seasons, established and defended territory through multiple competitive encounters, hunted hundreds or thousands of individual prey animals, and experienced the full range of Cretaceous Patagonian weather and season and ecological change that its world could offer. The depth of experience that such a lifespan represents, even for an animal whose cognitive life was very different from our own, is worth pausing to appreciate. Let the image of that long life spread gently in your mind. The hatchling in the first morning of its existence, small and bright-eyed and full of a life not yet tested. The juvenile navigating the dangers of a world in which it was prey as much as predator. The young adult finding its first territory, establishing its first horned dominance over rivals, experiencing its first successful hunt of substantial prey. The mature animal in its prime, settled and confident, the landscape of its territory as familiar as your own neighborhood, the rhythms of the seasons and the prey and the rivals as familiar as the rhythms of your own life. And at the end, the old animal, its horns worn and its hide scarred with the accumulated marks of decades of territorial competition and hunting, resting in the warm afternoon of a world that had held its kind for millions of years and would continue to hold them for millions more. Sleep, if you are ready, can come now. The story will continue, gently, in the background of whatever dreams find you. The broader family of abelisaurid dinosaurs, of which Carnotaurus is the most famous and most dramatically ornamented member, deserves extended consideration because understanding the family in its full diversity helps illuminate what Carnotaurus was and what made it distinctive even within its own evolutionary lineage. The abelisaurids were not confined to South America, though South America was their heartland and produced their most spectacular forms. They were, as we have touched upon, a truly global radiation across the Gondwanan landmasses of the Cretaceous, and the variety of forms they took in different environments on different continents is a fascinating study in how the same basic evolutionary body plan can be modified and elaborated in different directions by the particular selective pressures of different environments. Majungasaurus crenatissimus, from the Late Cretaceous of Madagascar, is in many ways the best-known abelisaurid after Carnotaurus, known from extraordinarily abundant material that includes multiple skulls and essentially complete skeletal elements. Majungasaurus was a large predator of similar overall size to Carnotaurus, with the characteristic blunt skull and reduced forelimbs of the abelisaurid family, but its cranial ornamentation took a very different form. Instead of the paired lateral horns of Carnotaurus, Majungasaurus had a single rough-surfaced dome of bone on the top of its skull, superficially resembling the cranial domes of the pachycephalosaurs, but completely independent in its evolutionary origin. The discovery of this dome and the subsequent analysis of its structure and the mechanics of the skull suggested to some researchers that Majungasaurus engaged in head-to-head combat or head-butting in intraspecific competition, using the dome as a battering ram in the way that pachycephalosaurs have been proposed to use their domes, though this interpretation has also been questioned by researchers who point out the relatively thin construction of the dome compared to what would be expected for a genuine battering weapon. The Madagascar that Majungasaurus inhabited in the Late Cretaceous was an isolated island that had been separated from the African mainland for tens of millions of years, and the fauna of that ancient Madagascar was in many ways as distinctive and as evolutionarily isolated as the fauna of modern Madagascar, which retains remarkable biological uniqueness today as a result of its long history of island isolation. The prey available to Majungasaurus was different from the titanosaur fauna of Patagonia, consisting primarily of titanosaur sauropods of local Madagascar endemics, and the remarkable group of sauropods called the saltosaurids, which in some species had extensive bony armor embedded in their skin. Hunting armored prey would have required different attack strategies from hunting the less armored titanosaurs of South America, and whether the skull morphology and body proportions of Majungasaurus reflected adaptations to its specific prey community is a question that researchers have explored with considerable interest. One of the most remarkable aspects of the Majungasaurus record is the evidence for cannibalism. Bones of Majungasaurus have been found with tooth marks matching the teeth of Majungasaurus, providing direct fossil evidence that these animals fed on members of their own species. Whether this represents predation of living individuals or the scavenging of already dead animals is not clear from the evidence alone, but either way, it tells us something important about the ecology and opportunistic feeding behavior of this abelisaurid. Cannibalism in large predators is not unusual in modern animals, ranging from the well-documented cannibalism of Komodo dragons to the occasional cannibalism of lions and crocodilians, and it typically occurs when prey resources are scarce or when the opportunity to consume a large, protein-rich carcass presents itself regardless of the species of the deceased. Rajasaurus narmadensis, from the Late Cretaceous of India, represents another fascinating branch of the abelisaurid family tree. India in the Late Cretaceous was in the process of one of the most dramatic geological journeys in the history of plate tectonics, having separated from the Gondwanan landmasses and drifted northward at a relatively rapid pace across the Tethys Ocean toward its eventual collision with Asia that would raise the Himalayas. This journey had profound implications for the fauna of India, which evolved in increasing isolation from other Gondwanan landmasses, even as it was approaching the Eurasian landmass that would eventually add northern biological influences to its fauna. The abelisaurids of India, including Rajasaurus, represent the phase of isolated Gondwanan evolution before the continental collision began to introduce new faunal elements from the north. Rajasaurus had a single nasal horn, rather than the paired lateral horns of Carnotaurus or the cranial dome of Majungasaurus, another variation on the abelisaurid theme of elaborated cranial ornamentation. The discovery of Rajasaurus from the Lameda Formation of Gujarat in India was particularly exciting for paleontologists, because it confirmed that the abelisaurid radiation had indeed extended to the Indian subcontinent during its long drift across the ocean. And it added another data point to the biogeographic story of how this family had spread from its Gondwanan origin across the fragmenting southern supercontinent. Carcharodontosaurus saharicus, which we discussed in the Spinosaurus narration as the co-inhabitant of the North African Chem-Chem ecosystem, was not an abelisaurid, but a Carcharodontosaurid, a member of a different family of large predatory dinosaurs that occupied the apex predator role in North Africa and South America during the Middle Cretaceous, before being replaced in some regions by abelisaurids during the Late Cretaceous. The distinction between Carcharodontosaurids and abelisaurids is an important one for understanding the biogeography of large theropod predators during the Cretaceous, and the transition from Carcharodontosaurid to abelisaurid dominance in some parts of the Gondwanan world is one of the interesting faunal turnover events of the Cretaceous that paleontologists are still working to understand. In South America specifically, there is a period during the early to middle part of the Late Cretaceous, roughly from around 90 to 80 million years ago, when the fossil record documents a transition from an ecosystem dominated by Carcharodontosaurid apex predators to one dominated by abelisaurids like Carnotaurus. This transition was not instantaneous, and the exact timing and mechanism are still being worked out as new fossil material is discovered and described, but it represents a genuine faunal replacement, a change in which family of large predatory dinosaurs held the ecological role of apex carnivore in the South American ecosystem, driven by the interactions of climate change, prey evolution, and the competitive dynamics between the two predator families. The final dominance of the abelisaurids in South America, with Carnotaurus as their most spectacular representative, was thus the outcome of millions of years of ecological competition and evolutionary change, a drama played out across geological time in the bones and teeth and footprints of animals that left only their most durable parts behind for us to find. The abelisaurids won not because they were inherently superior to the Carcharodontosaurids in every dimension, but because the particular combination of features they offered, their body plan, their hunting capabilities, their ecological flexibility, proved more adapted to the specific conditions of the Late Cretaceous Patagonian environment than the Carcharodontosaurid approach. The extinction of Carnotaurus and of all non-avian dinosaurs came at the end of the Cretaceous period, approximately 66 million years ago, in one of the most dramatic and well-documented extinction events in the history of life on Earth. The asteroid impact at Chicxulub, off the coast of what is now the Yucatan Peninsula of Mexico, released an amount of energy equivalent to billions of nuclear weapons, triggered global fires, blasted debris into the upper atmosphere that blocked sunlight for months or years, caused a global winter that collapsed photosynthesis-dependent food chains from the base up, and ultimately drove the extinction of approximately 3/4 of all species on Earth, including all non-avian dinosaurs. Carnotaurus, living on the other side of the world from the impact site in South America, would not have experienced the immediate catastrophic effects of the impact itself, the tsunamis and the blast wave and the initial fires. But the global climate disruption that followed the impact, the months of darkness and cold, the collapse of the plant communities that supported the Titanosaurs supported Carnotaurus, the failure of the food chain from the bottom up would have reached South America within weeks and would have made the survival of any large land predator essentially impossible. The last Carnotaurus, whatever it was doing in whatever quiet corner of Patagonia it occupied when the world changed, would not have had any way to understand what was happening. It would simply have noticed that the titanosaur herds were thinning, that the prey was becoming harder to find, that the vegetation was failing, and it would have persisted as long as its body mass reserves allowed before joining the overwhelming majority of its kind in a final, uncomprehending death. This ending is not a failure of Carnotaurus or of the Abelosaurid family. It is a testament to the arbitrary cruelty of cosmic chance, the way in which a single extraterrestrial event can overwhelm the most magnificently adapted biological machinery that millions of years of evolution have produced. Carnotaurus had been magnificently well adapted to its world. It had been doing everything right, everything that natural selection had shaped it to do, and it had been doing it successfully for a very long time. The extinction that claimed it claimed the most successful and the least successful alike, the apex predator and the smallest insect-eating mammal in the same sweeping catastrophe. That mammals survived and non-avian dinosaurs did not reflects not the superiority of mammals, but the accident of body size and metabolic rate and the particular ecological niches that happened to offer refugia from the catastrophic conditions that followed the impact. And yet the Abelisaurids, in the broader evolutionary sense, did not end without leaving descendants. The birds that fill our skies today, those 400 billion feathered descendants of theropod dinosaurs, are not the descendants of Abelisaurids specifically, but they carry in their bones and their biology the deep evolutionary heritage of the theropod lineage to which Carnotaurus also belonged. Every bird is a theropod dinosaur, though very few of them have bullhorns. Every bird's song is, in the deepest evolutionary sense, an echo of the Mesozoic world. And when you hear a bird call in the early morning, there is something in that sound, however transformed by 66 million years of bird evolution, that is connected by unbroken lineage to the vocalizations, whatever they were, of the predators that called across the Patagonian floodplains when the world was young and warm and full of giants. Let this thought settle gently into the quieter spaces of your mind, the thought of connection, of evolutionary lineage stretching from the late Cretaceous of Argentina to the birds outside your window, passing through the catastrophe of the end Cretaceous extinction and emerging transformed into the extraordinary diversity of modern avian life. The thread is unbroken, however changed. And somewhere in that thread, however faint the echo, is Carnotaurus. The geological record that preserves the story of Carnotaurus is itself a story worth telling, because it illuminates the processes through which we come to know anything at all about the deep past, and helps us understand both the richness and the limitations of what the fossil record can tell us. The Chorrillo Formation, from which the original Carnotaurus specimen was recovered, is a geological unit of Late Cretaceous age, deposited in the environment of river floodplains and delta systems that characterized much of Patagonia during this period. The formation takes its name from the Chorrillo River in the Chubut province of Argentina, and it is part of the larger geological sequence of Late Cretaceous sedimentary rocks that crop out across a broad region of Patagonia, providing a rich and relatively continuous record of the environmental and biological history of the region during the final tens of millions of years of the age of dinosaurs. Sedimentary rocks like those of the Chorrillo Formation are formed by the accumulation and lithification of particles deposited by wind, water, or other geological agents. In the case of the Chorrillo Formation, the dominant depositional processes were the deposition of sediment by rivers flooding their banks during wet seasons, and the wind transport of fine particles during drier periods, creating a layered sequence of mudstones, sandstones, and siltstones that preserves a record of the environmental conditions at the time of each layer's deposition. Within these rock layers, the bones of animals that died in or near the depositional environment were occasionally buried before they could be entirely decomposed or scattered by scavengers and weathering. And over millions of years, the buried bones were slowly replaced by minerals from the surrounding sediment in the process of permineralization, converting them into the durable fossil material that paleontologists find today. The rarity of fossil preservation, the fact that only a tiny fraction of animals that ever lived leave any fossil trace at all, is something that cannot be overemphasized in any honest account of what the fossil record represents and how it should be interpreted. The vast majority of organisms that have ever lived decomposed without leaving any trace in the geological record. Of those that did leave traces, the vast majority left only fragmentary material. A tooth here, a fragment of bone there, insufficient to reconstruct the living animal with any confidence. The number of species known from truly excellent, essentially complete specimens like the Carnotaurus holotype is tiny compared to the number of species that are known only from teeth or isolated bones, and those in turn are a tiny sample of the total diversity of life that existed across the hundreds of millions of years of complex animal evolution. What this means for our understanding of Carnotaurus is that the single known specimen from the Chorrillo Formation almost certainly does not represent the full range of variation within the species. There were almost certainly differences between individuals, differences in size, in the precise shape of the horns, in the coloration of the skin, in the proportions of various body parts that reflect the normal biological variation within any animal population. We are looking at one individual and drawing conclusions about a species, which is a necessary but potentially misleading exercise in inference that good scientists approach with explicit acknowledgement of its limitations. There may also have been more than one species within the genus Carnotaurus. The genus is currently known from a single species, Carnotaurus sastrae, based on the single known specimen, but the possibility that related species existed in nearby geographic areas or at slightly different time periods is very real. And future fossil discoveries in Patagonia and elsewhere in South America could reveal a previously unknown diversity within the Carnotaurus lineage. Paleontological knowledge is not a closed book, but an ongoing accumulation. And each new field season in Patagonia, each new quarry opened in the dusty hillsides of the Chubut province, has the potential to add fundamentally new information to the picture of late Cretaceous South American life. The techniques that modern paleontologists bring to the study of specimens like the Carnotaurus holotype have advanced enormously since Bonaparte first described the animal in 1985. Computed tomographic scanning, which uses X-rays to create detailed three-dimensional images of the internal structure of fossils without the destructive cutting that earlier researchers had to resort to, has been applied to the Carnotaurus skull and has revealed details of the internal anatomy, including the brain cavity and the paths of cranial nerves and blood vessels that were not accessible through surface examination alone. These internal details have contributed to our understanding of the sensory capabilities of the animal, the size and organization of different brain regions, and the vascular anatomy of the skull in ways that purely external examination could not provide. Geometric morphometrics, the mathematical analysis of shape and shape variation using landmarks placed on specimens, has been used to compare the skull of Carnotaurus with those of other abelisaurids, and to quantify the similarities and differences in a rigorous, statistically tractable way. These analyses have confirmed the phylogenetic relationships of Carnotaurus within the abelisaurid family, and have illuminated the degree of morphological diversity within the family, showing that the various skull forms seen in different abelisaurid genera, from the horned skull of Carnotaurus to the domed skull of Majungasaurus to the single-horned skull of Rajasaurus, represent genuine discrete morphological strategies rather than a simple continuum of variation. Bone histology, the microscopic examination of thin sections of fossil bone, has been applied to various theropod dinosaur specimens, and the results applied by inference to Carnotaurus, revealing the patterns of bone deposition and remodeling that reflect the growth rate and metabolic physiology of the living animal. The bone histology of large theropod dinosaurs consistently shows patterns that are more similar to those of modern birds and mammals, with their elevated metabolic rates, than to those of modern reptiles, suggesting that non-avian dinosaurs, including the abelisaurids, were metabolically active animals with significantly higher growth rates than modern ectothermic reptiles of comparable size. The implications of this elevated metabolism for the daily life of Carnotaurus are significant. A metabolically active animal requires more food per unit body mass than an ectothermic animal of the same size, which in turn means that a high metabolism predator must hunt more frequently and more successfully to sustain itself. The flip side of this higher energy requirement is a higher capacity for sustained activity, the ability to maintain high output locomotion for longer periods than an ectotherm could manage, which is precisely the capability that a pursuit predator needs for the kind of sustained chase and repeated high-speed attack that the anatomy of Carnotaurus suggests. The elevated metabolism and the pursuit predator body plan are thus not independent features of Carnotaurus, but aspects of an integrated biological system in which each feature supports and enables the others. The question of whether Carnotaurus was fully endothermic, generating all its own body heat through metabolic processes as modern birds and mammals do, or whether it occupied some intermediate metabolic state using a combination of metabolic heat generation and environmental heat uptake to maintain its body temperature, is one that is still being actively researched in the context of non-avian dinosaur biology generally. The evidence from bone histology, from body size, and from the ecological requirements of large active predators all point toward a metabolic physiology significantly elevated above that of modern ectothermic reptiles. But whether it was indistinguishable from full endothermy in the manner of birds and mammals, or occupied some intermediate position, is a nuanced question, without a fully settled answer. What we can say with confidence is that Carnotaurus was not a slow, torpid, cold-blooded creature in the old Hollywood mold, waiting in the sun to warm up before it could move, spending most of its time in behavioral thermoregulation rather than active predation. It was a genuinely active, metabolically capable animal, able to run fast, hunt effectively, maintain territorial ranges of considerable extent, and sustain all the energetic demands of a complex predatory life in a warm, productive Cretaceous ecosystem. This active, warm-blooded vision of Carnotaurus is not a recent invention of paleontological fashion, but an evidence-based conclusion from the accumulated work of researchers examining the biology of non-avian dinosaurs from multiple angles over several decades. Now, let the world of Carnotaurus expand a little further in your imagination. Beyond the individual animal and beyond the immediate ecosystem, think about what it means that this animal existed at all. What it says about the extraordinary creativity of the evolutionary process and about the diversity of paths that life can take when given sufficient time and sufficient environmental pressure. In the late 19th and early 20th centuries, when the science of paleontology was young and the first large theropod dinosaurs were being described and reconstructed for museum halls, there was an implicit assumption that large predatory dinosaurs were essentially variations on a theme, different sizes and proportions of the same basic design. The Tyrannosaur model, the large, bipedal, big-jawed meat-eater, was treated as the template against which all other large theropods were measured. Carnotaurus demolished this assumption completely and permanently. Here was a large predatory dinosaur that was not trying to be a tyrannosaur. It was not trying to be anything that anyone had imagined. It had evolved its own solution to the problem of being a large predator, a solution involving speed rather than bulk, slicing teeth rather than bone-crushing jaws, elaborate cranial display structures rather than simple functional efficiency, and a body plan so distinctive in its proportions and its ornamentation that it could never be mistaken for any other animal that has ever lived. It was, in the deepest sense itself, the product of millions of years of evolution in a world that was going its own way, making its own experiments, finding its own answers to the eternal questions of how to eat and survive and reproduce in a complex, dangerous, and endlessly changeable world. This, finally, is perhaps the deepest gift that the story of Carnotaurus offers to anyone who spends time with it. Not just the fascinating facts of its anatomy and its ecology, not just the remarkable story of its discovery and the science that has grown around it, but the deeper lesson about the nature of life and evolution and possibility. Life does not have one solution. It has many. It finds them in unexpected places, through unexpected combinations, in animals that should not work by any prior expectation, but that work magnificently in the specific context that shaped them. Carnotaurus should not have worked. A large predator with tiny, useless arms and blunt, squarish skull and bull horns and a body built for speed rather than power is not what anyone would have designed from first principles. And yet it worked. It worked beautifully. For millions of years, in one of the most productively dangerous environments that the Cretaceous world produced. The world is always stranger and richer and more surprising than we expect. This is the message that comes up from the rock of Patagonia every time someone with patience and knowledge and a brush uncovers a bone that has been waiting for 70 million years. It is a message worth carrying into sleep, into the quiet space where the mind lets go of the day's certainties and opens to the larger, stranger, more wonderful reality that surrounds us. Let the warm Patagonian light fade slowly in your mind. Let the distant dinosaurs lower their heads to graze. Let the river move through its channel, unhurried, carrying the red Cretaceous silt toward a sea that no longer exists. And let Carnotaurus, the bull-horned predator, settle into the long grass of the floodplain with the slow dignity of a creature that knows its own power and has no need to prove it. Resting in the warm afternoon of a world that is gone, but that left its mark in stone for us to find and wonder at. The day is done. The story settles, and sleep can come. There are dimensions of the Carnotaurus story that we have not yet fully explored, and in the quiet of this evening, with the world softening around you and the day's concerns drifting gradually away, this is perhaps the perfect time to let those dimensions unfold slowly and without urgency. We have talked about the animal's anatomy, its discovery, its hunting strategies, its ecological context. Now let us spend some time with the questions that do not have clean answers, the genuine scientific uncertainties that make Carnotaurus not a closed case, but an open invitation to continued curiosity and continued investigation. Because the best science is not the science of settled answers, but the science of well-framed questions. And Carnotaurus offers several questions so well-framed and so deeply interesting that they could occupy a scientist for an entire career. The first and most persistent of these questions concerns the precise function of those remarkable horns. We have touched on this already, considering the display, intraspecific combat, and prey capture hypotheses in turn. But the question deserves deeper consideration because the answer, or rather the gradual approach toward a more confident answer that science represents, requires thinking carefully about what kinds of evidence can actually bear on a question of this kind. We cannot observe Carnotaurus using its horns. We cannot run behavioral experiments with living animals. We are left with the bones themselves, with what they can tell us about the mechanics of the structures they supported, and with the broader biological and ecological context that helps us reason by analogy from what we know of living animals. One approach to this question that has been fruitful is the comparative approach. Looking at the variety of cranial ornamentation seen across the abelosaurid family, and asking whether the patterns of variation make more sense under one functional hypothesis than another. If the horns were primarily for prey capture, we might expect them to be most developed in animals that hunted the largest and most dangerous prey, since that is when a weapon attached to the skull would be most useful. If the horns were primarily for intraspecific display and combat, we might expect them to show more variation between species in terms of specific shape, while sharing a consistent, robust structure suited to force absorption, since species-specific display signals need to be distinguishable, while the mechanical demands of actual combat are similar across species. If the horns were primarily for thermoregulation, we might expect them to be larger in animals living in hotter, more strongly seasonal climates. The pattern seen across abelosaurids does not cleanly support any single hypothesis. Different abelosaurid species have very different cranial ornamentation, from the paired lateral horns of Carnotaurus to the single nasal horn of Rajasaurus, to the cranial dome of Majungasaurus, to the elaborate crests and knobs of other species, suggesting that these structures were evolving rapidly and diversely within the family, as display structures typically do. The robust, reinforced structure of the Carnotaurus skull, particularly around the orbital region where the horns attach, is consistent with force absorption in combat situations. And the vascular channels that have been identified in the skull bones near the base of the horns, in some analyses, suggest a good blood supply to these structures, which could support either thermoregulatory function or the tissue growth and maintenance of actively used combat structures. The most likely conclusion, and it is the kind of probabilistic conclusion that science is usually limited to when dealing with extinct animal behavior, is that the horns of Carnotaurus served multiple functions simultaneously. Display and species recognition, intraspecific combat, and possibly some thermoregulatory contribution may all have been part of the horn's biological role, with the relative importance of each function varying with circumstances and with the life stage of the animal. This kind of multifunctional interpretation is actually very common in biology, since natural selection tends to co-opt existing structures for additional functions rather than building single-purpose organs when a structure already exists that can be modified to serve multiple needs. The horns were almost certainly not primarily prey capture devices, but they were almost certainly display and combat structures, and the possibility that they contributed to thermoregulation in some capacity cannot be excluded. The question of thermoregulation in Carnotaurus is itself a larger question about how a large predator in a warm, seasonal environment managed its body temperature across the range of conditions it encountered. In the warm Patagonian summers, maintaining a stable body temperature would have required some mechanism for shedding excess heat, and the possibilities available to a large dinosaur included behavioral thermoregulation, such as seeking shade or water, physiological mechanisms, such as panting or evaporative cooling through moist surfaces, and structural features that increase the surface area available for heat dissipation. The textured, tuberculated skin of Carnotaurus, with its increased surface area compared to a smooth surface, may have contributed to heat dissipation in addition to its other possible functions such as camouflage or water retention. The question of how Carnotaurus managed water balance, particularly during the dry seasons of the Patagonian climate cycle, is another area of interesting inquiry. Large predators in modern seasonal environments have various strategies for managing water balance during dry periods, ranging from obtaining water from their prey to making physiological adjustments that reduce water loss to actively seeking and using water sources in the landscape. The kidneys of reptiles and birds are capable of producing highly concentrated urine, reducing water loss relative to the kidneys of mammals, and if Carnotaurus had a similar physiological capability, it would have been relatively well adapted to the seasonal water stress of a semi-arid environment. The proximity of river systems and lakes in the Patagonian landscape would have provided access to water during even the driest periods for an animal large enough and fast enough to travel the distances required to reach those water sources. The reproductive biology of Carnotaurus is almost entirely unknown from direct evidence. No eggs attributable to Carnotaurus with confidence have been described, and no nesting sites or associated reproductive behavior has been preserved in the fossil record in a way that can be linked to this specific animal. We can infer from phylogenetic reasoning that Carnotaurus, like all dinosaurs, reproduced by laying eggs, and from the general biology of large theropods, we can suggest that clutches were probably not enormous, that the eggs were probably relatively large relative to the size of typical dinosaur eggs in proportion to the adult body size, and that some form of nest construction and possibly parental care were involved in reproduction. But these are inferences from general dinosaur biology rather than observations specific to Carnotaurus, and they should be held with appropriate tentativeness. The possibility of parental care in abelosaurids is an interesting question that the fossil record has not yet definitively resolved. In modern archosaurs, which include both birds and crocodilians, parental care is the norm rather than the exception. Birds invest enormously in incubating and raising their young, and crocodilians are notable among modern reptiles for their active nest guarding and assistance of hatchlings in reaching water. If the ancestral archosaur condition included some form of parental care, as the behavior of modern archosaurs suggests, then abelisaurids like Carnotaurus may well have shared this ancestral tendency. The enormous investment required to produce eggs and the vulnerability of hatchlings in a world full of predators would have created strong selection pressure for any behavior that increased the survival of offspring, including nest guarding, egg incubation, and possibly the care of young animals during the most vulnerable period of their early growth. The social structure of Carnotaurus populations is another dimension of its biology that we cannot observe directly but can reason about from ecological principles and from what we know about the social behavior of large modern predators in comparable ecological settings. We have already discussed the strong likelihood of territorial behavior in adults, driven by competition for prey resources and potentially by competition for mates. The question of whether Carnotaurus was entirely solitary within its territory, interacting with conspecifics only during the breeding season and in territorial encounters, or whether some degree of social tolerance or even social organization was possible, is one that the evidence cannot resolve, but that the biology makes interesting. Some large modern predators that were traditionally assumed to be solitary have been found, through advances in tracking and observation technology, to have more complex and nuanced social lives than previously recognized. Tigers, long considered the archetype of the solitary predator, have been found to have extended social bonds between mothers and offspring, to tolerate the presence of relatives in overlapping ranges, and to interact in ways that go beyond pure competition in certain circumstances. If Carnotaurus had comparable complexity in its social interactions, the daily life of these animals in their floodplain environment may have been more socially nuanced than the simple territorial solitary model suggests. The interactions between Carnotaurus and the other animals of its ecosystem extended, of course, far beyond the predator-prey and competitor relationships we have already discussed. Every animal exists within a web of ecological relationships that includes parasites, symbionts, scavengers, and the many indirect interactions mediated through shared resources and shared environmental influences. The parasites of Carnotaurus, the internal and external organisms that would have lived on and within its body, extracting nutrition from the host, are almost completely invisible in the fossil record. But they were certainly present and were almost certainly a significant factor in the health and fitness of individual animals. Modern large predators carry substantial parasite burdens, from intestinal worms to blood parasites to external arthropods, and there is no reason to think large Cretaceous predators were any different. The scavengers that attended the kills of Carnotaurus, consuming what the primary predator left behind, were an important component of the ecosystem, helping to cycle nutrients back into the soil and preventing the accumulation of potentially disease-causing carcasses in the landscape. Small dinosaurs, pterosaurs, and possibly the crocodilians of the river systems would all have been capable scavengers, and the carcass of a large titanosaur killed by Carnotaurus would have supported a diverse and energetically significant community of secondary consumers for days or weeks after the initial kill. The role of invertebrates in the Carnotaurus ecosystem is also worth considering, because the invertebrate community of any terrestrial ecosystem performs essential ecological functions that support the entire food web. The insects, worms, mollusks, and other invertebrates of late Cretaceous Patagonia were processing organic matter, cycling nutrients, pollinating plants, and providing food resources for small vertebrates that in turn provided food for larger animals. The diversity of late Cretaceous insects, already quite high by the Cretaceous period, with the major modern insect orders either established or in their early diversification, would have included many familiar functional types, including decomposers, pollinators, predators, and parasites, all performing the same broad ecological roles that their modern counterparts perform today. The plants of the ecosystem performed, as they always do, the foundational work of capturing solar energy and converting it into biological material that all the animals of the ecosystem, directly or indirectly, depended upon. The angiosperms that were diversifying in the late Cretaceous, spreading across the landscape and beginning to dominate the lower levels of the vegetation, were not just passive food sources, but active participants in the ecology of the ecosystem, evolving defenses against herbivores, attracting pollinators with flowers and fruiting bodies, establishing mutualistic relationships with soil microorganisms that enhanced nutrient uptake and plant growth. The coevolutionary relationships between the angiosperms and the herbivorous dinosaurs that fed on them, and between those herbivores and the predators that hunted them, were the kind of complex, multi-species interactions that define the character of any mature ecosystem. The soil itself, the microbiome of bacteria, fungi, and other microscopic organisms that break down organic matter and make nutrients available to plants, was the foundation on which the entire ecosystem rested. And the health and diversity of the soil community determined the productivity of the plant communities, that in turn determined the abundance of herbivores, and ultimately of predators like Carnotaurus. The web of life in late Cretaceous Patagonia was, in this sense, not just the visible drama of large animals interacting in dramatic ways, but a vast and mostly invisible world of microbial activity, nutrient cycling, chemical signaling, and ecological process that sustained everything visible from the bottom up. This humbling perspective that even the apex predator, even the most powerful and distinctive animal in its ecosystem, was sustained by and dependent upon an invisible world of microbes and chemical processes, is one of the most important insights that ecology has produced in the modern era. No living thing is truly independent. Every organism, from the most powerful predator to the smallest bacterium, exists within a web of dependencies and relationships that it cannot escape and could not survive without. Carnotaurus depended on titanosaurs. Titanosaurs depended on plants. Plants depended on soil microbes and sunlight and rain. Rain depended on ocean evaporation and atmospheric circulation patterns, and so on, in a web so intricate and so far-reaching that no single mind can hold it whole. What we can do is hold a piece of it, a beautiful and interesting piece, and feel through that piece the presence of the whole. The piece we have been holding is Carnotaurus, the bullhorn predator of late Cretaceous Patagonia, an animal of extraordinary physical distinction and ecological success, whose story connects us to a world so different from our own that exploring it feels like travel to another planet, and yet whose story is also, in the deepest sense, continuous with our own. Part of the long, unbroken thread of life on Earth that stretches from the first single-celled organisms in the ancient ocean to the extraordinarily complex and various living world of today. The rock of Patagonia continues to give up its secrets slowly, one fossil at a time, one field season at a time. New abelisaurid species are being described with increasing frequency as paleontological work in South America, Africa, Madagascar, and India intensifies, and each new species adds detail and nuance to the picture of this remarkable family of predators. New analytical techniques continue to extract information from existing specimens that earlier generations of researchers could not access, and the accumulated understanding of Carnotaurus and its relatives grows richer and more detailed with each passing year. The original Carnotaurus specimen, the bones that Bonaparte pulled from the Patagonian hillside in 1984, now resides in the Argentine Museum of Natural Sciences, Bernardino Rivadavia in Buenos Aires, where it is one of the most prized specimens in a collection of extraordinary scientific value. Buenos Aires, the city of wide boulevards and European architecture and tango music, drifting from open windows on warm evenings, holds in its Natural History Museum the bones of one of the strangest predators that this planet has ever produced, waiting there in the quiet of a museum night, while the city moves and breathes and sleeps above it. The bones that walked the Patagonian floodplain 70 million years ago rest now in the capital of the country where they were found, in the care of the scientists and institutions of the nation whose landscape produced them. And that continuity of place, that connection between the ancient bones and the modern city that has grown above the ancient rock, is itself a kind of poetry. Argentina has a particular and deep relationship with paleontological science that is not always fully appreciated outside of the specialist community. The country has produced some of the most extraordinary dinosaur discoveries of the modern era, from the titanosaur giants of Patagonia to the early dinosaur ancestors of the Triassic period in the Northwest, from the abelisaurid predators of the Cretaceous to the remarkable pterosaurs of various Mesozoic formations. This richness of the Argentine fossil record reflects both the geological history of the South American continent, which preserved an exceptional record of Mesozoic life in its sedimentary rocks, and the dedication and skill of the Argentine paleontologists who have worked those formations across generations, from Bonaparte and his contemporaries to the current generation of researchers who continue to make extraordinary discoveries in the dusty hillsides of Patagonia. The tradition of paleontological excellence in Argentina is in many ways inseparable from the tradition of scientific wonder. The deep human impulse to look at a bone in the rock and ask what it was, what it tells us, what world it came from, and what that world can teach us about our own. This impulse is not limited to scientists. Every person who has ever stopped at a museum display case to look at a fossil, every child who has ever picked up a rock that looked different from the others and wondered what it was, every person listening now to the quiet story of Carnotaurus and feeling the pull of that ancient world is participating in the same fundamental human activity of reaching backward through time and touching the reality of the past. The past is not gone. It is present in everything around us, in the rocks beneath our cities and our fields, in the DNA of every living organism that carries within it the molecular record of billions of years of evolution, in the bones and teeth and skin impressions of animals like Carnotaurus that left their marks in the rock of Patagonia and waited patiently for the curious descendants of the small mammals that had shared their world to come looking. The past is patient, it can wait. And perhaps that patience, that vast and unhurried waiting of geological time, is itself a comfort in the quiet of the evening. In the long story of this planet, the troubles and urgencies of a single day are very small things, held within a context of such enormous depth and such extraordinary richness that to become aware of that context, even briefly, even partially, is to feel a kind of peace that nothing else quite provides. The dinosaurs of Patagonia, the titanosaurs and the abelisaurids and the pterosaurs and all the rest, lived their full and complex lives in a world they could not have imagined the end of. And yet the world ended and was replaced, and life continued as it always has, finding new forms and new strategies and new wonders in the space left by what had passed. Sleep now, if sleep will come. Let the Patagonian night settle over the floodplain of your imagination. Let the river murmur through its channel in the dark. Let the titanosaurs stand quiet in the blue-black of a Cretaceous night, and let Carnotaurus rest somewhere in the long grass, its bullhorns pale in the moonlight, breathing slowly, present and complete in its ancient world, a creature of such strange beauty that even the rock could not entirely let it go. The science of paleontology and the study of Carnotaurus within it is not merely the cataloging of ancient bones, but a deep and ongoing conversation between the human mind and the physical record of life's history on Earth. This conversation has been going on for only a few centuries in any recognizably scientific form, and for Carnotaurus specifically, it has been going on for less than half a century since Bonaparte's initial discovery. But the conversation is accelerating, becoming richer and more detailed with each passing decade, as new specimens are found, new methods are developed, and new researchers bring fresh perspectives to old questions. The community of researchers who study abelisaur dinosaurs has grown substantially since the 1980s, when Carnotaurus was first described and the abelisaurid family was still poorly known. Today, teams working in Argentina, Brazil, Madagascar, India, Italy, the United States, and several other countries are actively engaged in the description of new specimens, the analysis of existing material with new methods, and the development of broader synthetic understanding of the abelisaurid family's evolutionary history, biogeography, and ecological diversity. The scientific publications emerging from this community appear with increasing frequency, each one adding some piece of the larger puzzle. And the cumulative picture of the abelisaurids that is emerging is significantly richer and more nuanced than anything that could have been imagined when Carnotaurus was first named. New abelisaurid species are being described at a rate that would have seemed remarkable to the paleontologists of the 1970s, who knew this family only from the poorly preserved material of Abelisaurus itself. In the decades since the description of Carnotaurus, species have been named from Argentina, Brazil, Niger, Morocco, Madagascar, India, and possibly Europe, expanding the known geographic range of the family and documenting the diversity of forms it produced across the Gondwanan world. Each new species adds a data point to the biogeographic and evolutionary analysis of the family, helping researchers trace the routes of dispersal, identify the patterns of diversification, and understand the ecological relationships between different abelisaurid lineages in different parts of the world. Particularly exciting have been the discoveries of abelisaurids from the Triassic and Jurassic periods, earlier than had previously been documented for the family. While the peak of abelisaurid diversity was clearly in the Cretaceous, the discovery of potential earlier members of the lineage has pushed the origin of the family back in time and has important implications for understanding the biogeographic history of Gondwana and the timing of the initial dispersal of abelisaurids across the separating continental fragments. Each such discovery requires a revision of the evolutionary tree, a new round of phylogenetic analysis to determine where the new species fits in the broader family relationships. and a new look at what the revised evolutionary picture implies for the biogeographic and ecological history of the group. The phylogenetic methods used to determine the evolutionary relationships of abelosaurids have themselves evolved dramatically since the 1980s. Early phylogenetic analyses of theropod dinosaurs used relatively simple methods, comparing a limited set of anatomical characters across a limited number of species. And the results, while valuable for their time, were inevitably limited by the available methods and the available data. Modern phylogenetic analyses use much larger data sets of anatomical characters, increasingly sophisticated mathematical methods for searching the space of possible evolutionary trees, and where possible, molecular data from ancient DNA or ancient proteins to supplement the morphological evidence. The result is a more robust and more detailed understanding of the relationships between species, not perfect, not free of uncertainty, but significantly more reliable than what was possible a generation ago. The question of where exactly Carnotaurus fits within the abelosaurid family tree has been addressed in multiple analyses with somewhat variable results, reflecting the genuine complexity of determining relationships from skeletal material that is variably preserved and variably studied. Most analyses place Carnotaurus within the subfamily Carnotaurini, a grouping that includes several South American abelosaurids that share certain skeletal features, distinguishing them from the other abelosaurid subfamily, the Majungasaurinae, which includes the Madagascar and Indian forms. This division of the abelosaurids into two main lineages, one centered in South America and the other in the eastern Gondwanan landmasses of Madagascar, India, and possibly Africa, reflects the biogeographic separation of these regions that occurred as Gondwana fragmented, and it provides a framework for understanding how the abelosaurid family diversified differently in different parts of the ancient southern world. The relationship between morphological diversification and ecological diversification in the abelosaurids is a question of fundamental interest to evolutionary biologists. Did different abelosaurid lineages evolve different skull shapes and body plans because they were adapting to different ecological niches, targeting different prey, or using different hunting strategies? Or did the morphological diversification reflect primarily non-ecological factors, such as sexual selection driving the rapid evolution of display structures like horns and crests, with the actual hunting ecology of different species being broadly similar? The answer, as is usual in complex biological systems, is probably both, with ecological adaptation driving some of the morphological variation and sexual selection driving some of the rest, the relative contributions varying between lineages and between specific characters. The horn of Carnotaurus, as we have discussed at length, is most plausibly primarily a sexual selection or competitive display structure, having evolved to its dramatic form through the advantages it conferred in intraspecific competition and mate attraction, rather than through direct improvements to prey capture efficiency. The overall body plan of Carnotaurus, its running adapted limbs and powerful neck and compact skull, reflects ecological adaptation to a specific predatory strategy in a specific prey environment. These two kinds of evolution, sexual selection and ecological adaptation, operated simultaneously on the Carnotaurus body plan, pulling it in directions that were compatible but not identical. And the result was the remarkable combination of features that we see in the known specimen. The role of sexual selection in the evolution of dinosaur morphology is a topic that has received increasing attention in paleontological research, partly because of the growing appreciation of how powerful sexual selection can be as an evolutionary force and partly because of the accumulating evidence that many of the most striking features of extinct dinosaurs, including crests, frills, horns, elaborate colors and patterns in feathered forms, and various other structures, are most parsimoniously explained as the products of selection for display and mate attraction, rather than direct functional adaptations for predation or defense. The work of paleontologists like Kevin Padian, Jack Horner, and their colleagues in arguing for the importance of sexual selection in dinosaur evolution has been controversial, but has also been genuinely stimulating to the field, prompting more careful thinking about the functional hypotheses we apply to unusual morphological structures. In the case of Carnotaurus, the horns are difficult to explain as direct improvements to predatory capability, given what we know about the mechanics of the skull and the hunting strategy implied by the rest of the body plan. A pursuit predator that catches prey with rapid bites and quick withdrawals does not obviously benefit from structures projecting from the top of its skull that would create drag during high-speed movement, and that were positioned above rather than in front of the jaws where they would be most useful in a prey capture role. The display and combat explanations, by contrast, are fully consistent with what we know about sexual selection in living animals and require no special pleading about unusual, predatory mechanics. The parsimonious conclusion, the conclusion that requires the fewest assumptions and is most consistent with the available evidence, is that the horns of Carnotaurus were primarily products of sexual selection, whatever secondary functions they may have served. The popular cultural life of Carnotaurus, the way this animal has been represented in films, books, games, and other media since its discovery, is itself an interesting dimension of its story that reflects both the genuine fascination that the animal inspires and the inevitable simplifications and distortions that occur when scientific subjects are translated into popular entertainment. The most famous popular depiction of Carnotaurus is probably the version that appeared in the 2000 Disney animated film Dinosaur, in which a pair of Carnotaurus serve as the primary antagonists, pursuing the film's iguanodontid protagonists across a dramatic post-apocalyptic landscape. The Disney Carnotaurus were depicted as fast, aggressive, and powerful, which is scientifically reasonable, but they were also depicted with certain artistic liberties that served the storytelling needs of the film rather than strict anatomical accuracy. The reception of Carnotaurus in the gaming world, particularly in various dinosaur-themed video games and role-playing games, has been broadly positive, with the animal's dramatic appearance and the excitement of its bullhorn imagery making it a natural subject for dramatic portrayal. Games often exaggerate the size and speed of Carnotaurus relative to other dinosaurs, turning it into something approaching a superhero among predators, which is understandable from an entertainment perspective, but somewhat at odds with the more nuanced ecological picture that paleontological science provides. In reality, Carnotaurus was a remarkable but not superhuman predator, fast and capable, but also limited by the same physical and ecological constraints that govern all large predators. The representation of Carnotaurus in serious popular science writing and documentary filmmaking has generally been more careful, though even here the demands of narrative and visual impact sometimes lead to emphases that do not perfectly reflect the weight of scientific evidence. The horns attract disproportionate attention because they are so visually dramatic and so immediately interesting to a general audience, sometimes at the expense of the other equally fascinating aspects of the animal's biology and ecology. The vestigial arms, the running adaptations, the skin evidence, the biogeographic context, the evolutionary relationships with other abelisaurids, all of these deserve equal billing with the horns in a complete account of the animal. But the horns are simply more immediately striking and more easily communicated in the brief formats that popular media favors. The challenge of communicating paleontological science to a wide audience without sacrificing essential nuance and honest uncertainty is one that good science communicators have been grappling with for decades. The temptation to simplify, to present confident narratives about what extinct animals looked like and how they behaved, is understandable when working in formats that reward confidence and clarity. But the most honest and ultimately the most interesting approach is to communicate the genuine uncertainty alongside the genuine knowledge. To invite the audience into the ongoing detective work of science, rather than presenting a completed picture that the evidence does not fully support. For Carnotaurus, the genuine knowledge includes the remarkable fact of its existence and its discovery, the detailed anatomy of the known specimen, the broad outlines of its ecological context and predatory biology, and its place within the evolutionary history of the abelisaurid family. The genuine uncertainty includes the precise function of the horns, the details of its hunting behavior, its social structure and reproductive biology, and many aspects of its physiology and sensory capabilities. Holding both the knowledge and the uncertainty simultaneously, appreciating what we know while being honest about what we do not, is the appropriate and rewarding stance for engaging with the science of any extinct animal, including Carnotaurus. One of the most remarkable and most underappreciated aspects of the Carnotaurus discovery is what it has done for the study of late Cretaceous South America more broadly. Before Bonaparte began his intensive work on the dinosaurs of Argentina in the 1960s and 70s, and before the flood of major discoveries that followed in subsequent decades, the late Cretaceous fauna of South America was almost entirely unknown. The isolation of South America as an island continent during the Cretaceous meant that its fauna was evolving in complete independence from the rest of the world. But the fossil record of that independent evolutionary experiment was almost entirely unexcavated. The discoveries that followed the Carnotaurus find transformed this situation entirely. Within a few decades of the 1980s, the late Cretaceous of Argentina had yielded not only Carnotaurus and the other abelisaurid predators, but the titanosaur giants including Patagotitan, Argentinosaurus, and Dreadnoughtus, each one contending for the title of largest land animal ever known. The remarkable small predator Alvarezsaurus and its relatives with their extremely modified forelimbs, the extraordinary sauropod Saltosaurus with its armored skin, and dozens of other species representing the full ecological range of a rich and distinctive Cretaceous ecosystem. The picture of late Cretaceous South America that has emerged from this work is of a continent full of biological wonders, an island world that had been making its own evolutionary experiments for tens of millions of years and had produced results of extraordinary diversity and strangeness. This picture continues to grow with each passing field season, as teams of researchers from Argentina and from institutions around the world continue to work the productive fossil beds of Patagonia and other Argentine provinces. New species are described regularly, new ecological relationships are documented, new biogeographic connections between South American and other Gondwanan faunas are clarified. The story of late Cretaceous South America is far from complete, and Carnotaurus, the bull-horned predator that opened the scientific world's eyes to the richness of that story, continues to occupy its central place in the unfolding narrative. The city of Neuquén in Argentina, the capital of the Neuquén province, where so many of the most important dinosaur discoveries have been made, has grown into a center of dinosaur science and dinosaur tourism that reflects the deep connection between the region's geological heritage and its modern cultural identity. The Museo Carmen Funes in the town of Plaza Huincul, not far from some of the most productive dinosaur sites, holds some of the most extraordinary dinosaur specimens in the world, including material of several giant titanosaurs that dwarf any dinosaur found on other continents. The Villa El Chocón Paleontological Museum holds material of the enormous Carcharodontosaurid predator Giganotosaurus, discovered in the 1990s and representing one of the largest predatory dinosaurs ever found. And the Argentine Museum of Natural Sciences in Buenos Aires, as we mentioned, holds the extraordinary Carnotaurus specimen that started so much of the modern understanding of South American Cretaceous life. Visiting these institutions, standing in front of the mounted specimens or the display cases holding the original material, is an experience that defies adequate description. There is something about the physical presence of a fossil, the knowledge that what you are looking at is the actual bone of an actual animal that lived and breathed and moved across the ancient landscape, that no photograph or computer model can fully replicate. The weight of the deep past becomes real in a way that words alone cannot achieve. And for anyone who has followed the story of Carnotaurus to this point, who has spent time imagining the bull-horned predator moving across its Patagonian floodplain, the encounter with the actual specimen in a Buenos Aires museum would be one of those moments of connection between imagination and reality that reminds us why the study of the ancient world matters. The study of the ancient world matters, ultimately, for the same reasons that any deep study of history matters. Not because the past can provide simple lessons that can be directly applied to the present, because it usually cannot, but because understanding the full depth and breadth of what has existed, what has lived and changed and died and been replaced, gives us a truer and richer sense of what is possible, what is fragile, and what is lasting about the world we inhabit. The dinosaurs of the Cretaceous, including Carnotaurus, are part of the longest and most complete story available to us, the story of life on Earth. And engaging with that story in the way that paleontological science makes possible is to become, in some small measure, a better inhabitant of the living world that story has produced. Let that thought carry you gently toward rest. The story of Carnotaurus is, in its deepest sense, a story about life's extraordinary capacity for invention, for finding new forms and new strategies in response to new challenges, for persisting through catastrophe and beginning again. It is a story that has been going on for hundreds of millions of years before the Carnotaurus appeared, and that has continued for the 66 million years since it disappeared. We are part of that story too, newcomers in geological terms, but inheritors of everything that came before us, our bodies and our brains and our capacity for wonder, all shaped by the long evolutionary history that stretches from the first life in the ancient ocean to this moment, this quiet moment, as you rest and the story settles into the comfortable dark. The floodplain is still. The river moves. The stars of a Cretaceous night, those same stars that are still there above us, though differently arranged by the slow drift of galactic time, look down on the sleeping form of the bull-horned predator. And somewhere in the rock, waiting with all the patience of stone, are the bones that will one day be found and named and studied and wondered at by the descendants of the small mammals that once shared the Patagonian night with Carnotaurus. never knowing what would come of their small, warm, persistent lives. The night is complete, the story is resting, and you can rest now too. In the deep quiet of the night, when the world has grown still and the mind begins its slow drift towards sleep, there's a particular kind of thinking that becomes possible. Not the sharp, purposeful thinking of the day, not the anxious planning and reviewing and deciding, but a softer, more wandering kind of thought. The kind that follows images rather than arguments, and that finds its way to unexpected places by routes that daylight logic would never travel. This is the kind of thinking that the story of Carnotaurus invites, because the story itself is full of unexpected places and routes that reason alone would never find. Consider, for a moment, the improbability of the entire enterprise. The improbability that an animal could have lived in all its specific and vivid reality 70 million years ago on a continent that is recognizably but not identically the continent we know today. The improbability that any trace of that animal's existence could have survived the erosion and chemical transformation and tectonic upheaval of 70 million years of geological time. The improbability that a human being in the late 20th century would happen to be working in the right province of Argentina at the right time, would recognize the significance of a bone eroding from a hillside, and would undertake the careful excavation and scientific description that transformed that bone into knowledge. And the further improbability that you, reading or listening to this story in whatever corner of the world you occupy, would come to know something true about an animal that has been gone from the earth for longer than any human concept of history can easily encompass. All of these improbabilities actually happened. They are facts, as solid and as real as any facts we have. And the fact of their actuality, the fact that the universe arranged itself in such a way that this particular animal, in this particular place at this particular time, left enough of itself behind for us to find and know and wonder at, is one of those facts that, when you really sit with it, opens something inside you that does not easily close again. The story of Carnotaurus is in this light not just a story about a dinosaur. It is a story about the deep connection between all things that have ever lived on this planet. The way in which the existence of any one organism is woven into the existence of all the others through the long thread of evolutionary history and the shorter thread of ecological dependence. Carnotaurus existed because of the titanosaurs that it hunted, which existed because of the plants that fed them, which existed because of the insects and microbes and soil chemistry and rainfall patterns and plate tectonic configurations that created the conditions for their growth. And we exist in part because of the Late Cretaceous extinction that killed Carnotaurus and all its kind, opening the ecological space in which our small mammal ancestors could diversify and eventually give rise to the vast and varied mammalian world of the Cenozoic. The age of mammals, the age that ultimately produced us. We owe our existence, in a very real evolutionary sense, to the catastrophe that destroyed the world of Carnotaurus. This is a strange thought to sit with. The asteroid that struck Chicxulub 66 million years ago was an unimaginable catastrophe for the life of the Cretaceous world, eliminating 3/4 of all species, including every non-avian dinosaur that had been the dominant large land animals for 160 million years. But it also cleared the ecological stage for the radiation of mammals that gave rise to every large land mammal alive today, including the primates, including the great apes, including the species of upright, curious, storytelling animal that has spent the evening thinking about a bullhorn predator from Patagonia. This connection between catastrophe and opportunity, between loss and the possibility of new beginnings, is one of the deepest patterns in the history of life on Earth. And the story of Carnotaurus and its extinction puts us in direct contact with that pattern in a way that is simultaneously humbling and reassuring. Humbling because it reminds us that our existence is contingent, that we are here not because we were inevitable, but because of a sequence of accidents and catastrophes and evolutionary experiments that could, at any of dozens of critical junctures, have turned out differently. Reassuring because it demonstrates that even the most catastrophic events in the history of life have been followed by renewal, by the emergence of new forms and new ecological relationships that were not possible in the world that existed before the catastrophe. Life persists. This is perhaps the most fundamental lesson of the fossil record. Read across 3.5 billion years of evolution from the first simple cells in the ancient ocean to the extraordinary complexity and diversity of today. Life is not fragile in the way that individual organisms are fragile. It is enormously resilient, enormously creative, enormously persistent in the face of conditions that seem, from any individual perspective, to be impossible to survive. The great mass extinctions of Earth's history eliminated the majority of species that existed at the time of each event, but none of them came close to eliminating life itself, and in the aftermath of each extinction, the surviving lineages diversified and expanded to fill the ecological space left by the casualties, producing new forms and new ecological relationships that were often as rich and as complex as what had existed before. Carnotaurus was not the last word of evolution in the Gondwanan landmasses, not even close. The Late Cretaceous of South America, rich as it was with titanosaur giants and abelosaurid predators and extraordinary flying reptiles, was itself only one chapter in an ongoing story of evolutionary experiment and ecological elaboration that continued before it and after it, right up to the end Cretaceous event that closed the Mesozoic chapter and opened the Cenozoic one. The story did not end with Carnotaurus. It transformed as it has always transformed, as it will continue to transform, for as long as this planet holds an environment hospitable to life. And we, the curious animals that have evolved the capacity to look backward through geological time and reconstruct the worlds that preceded us, are part of that transformation. We are the chapter that came after the Cretaceous, after the Paleocene and the Eocene and the Oligocene and the Miocene and the Pliocene and the Pleistocene, after all the ages of mammalian diversification and the great ice ages and the rise of our own genus. We are the animals that found the bones of Carnotaurus and asked what they were. We are the animals that look at the history of life and feel, alongside the information we absorb, a kind of wonder and gratitude that is distinctively ours, that no other animal we know of experiences in quite the same way. This capacity for wonder, for gratitude, at the sheer improbable richness of what exists and has existed, is worth protecting. It is one of the most valuable things we have, and one of the best ways to keep it alive is to do exactly what you have been doing, to spend time with the stories of the deep past, to let the ancient world become real in the imagination, to feel the pull of that vast and patient history, and let it remind you of the extraordinary privilege of being alive, conscious, and curious in a universe that is under no obligation to have produced anything as remarkable as you. The night deepens. The story of Carnotaurus has been told as fully as it can be told in the time we have had together. And there is more to tell, always more, because the science is ongoing and the fossils are still coming out of the rock, and the human capacity for wonder is not exhausted by any amount of information but only deepened by it. But for now, for tonight, what has been told is enough, and more than enough, and the rest can wait for another evening, another quiet hour, another slow drift towards sleep, with ancient worlds for company. Let the Patagonian floodplain recede into the comfortable distance of a dream. Let the titanosaurs become shapes in the warm mist. Let Carnotaurus, the bullhorned predator, the meat-eating bull of the Late Cretaceous, lower its magnificent strange head and close its lateral eyes, and rest in the deep grass of a world that is gone, and yet somehow, through the patient miracle of fossilization and the even more improbable miracle of human curiosity, is still here. Still real. Still capable of moving us across 70 million years of separation to something that feels very much like love for the strange and the ancient and the irrecoverably lost. Good night. Rest well. The bones are in the rock, the story is told, and the wonder, when you wake, will still be there, waiting for you, patient as stone. There is one more thread of this story that deserves to be unwound in the quiet of the evening, a thread that connects the deep past of Carnotaurus to the very specific and very immediate question of how the science of paleontology is done in the modern world, and why that work matters not just for its scientific content, but for what it represents about the human relationship with the planet and its history. Paleontological fieldwork in Patagonia is not a glamorous enterprise in the way that popular media sometimes depicts it. It is hard, physical, often frustrating work conducted in conditions that range from merely uncomfortable to genuinely harsh. In a landscape that is beautiful in its own austere way, but that offers very little in the way of the amenities that most of us take for granted in our daily lives. The wind in Patagonia is almost constant, a cold, dry wind that comes off the Andes and sweeps across the plateau without significant obstruction, carrying dust and fragments of rock and the occasional scent of the distant ocean. The sun at high altitude in the southern hemisphere is intense and can cause sunburn in hours. The terrain is rough, eroded into gullies and bluffs and scattered outcrops that require careful navigation on foot, and the work of locating, excavating, and documenting fossil material is slow, painstaking, and requires sustained attention and physical endurance. Paleontologists and their field assistants spend weeks or months at a time in this environment, living in camps that are often basic in their facilities, working from first light until the sun becomes too intense in the early afternoon, then returning to work as the light softens toward evening. The actual fossil discovery, the moment of recognizing a bone eroding from the surface of a cliff or hillside, is often the most dramatic part of the process, but is far from the most time-consuming. Once a fossil is identified and its significance assessed, the process of excavating it is measured in hours to weeks, depending on the size and fragility of the material and the depth of its burial. And every step of that process requires the kind of careful, patient attention that cannot be rushed without risk of damaging the irreplaceable material. The tools of fieldwork are simultaneously high-tech and surprisingly traditional. Computers and GPS units and satellite communication systems are now standard equipment in the field, allowing researchers to precisely document the locations of finds, to communicate with colleagues back in universities and museums, and to access databases of comparative material that would have required trips to multiple institutions in earlier decades. But the actual work of removing rock from around a fossil still relies on hammers and chisels and brushes and picks, on the direct manual skill of experienced preparators and researchers, who have learned through years of practice to read the rock and to know how much force to apply in each situation to expose bone without breaking it. The decision of how to proceed when a significant fossil is found involves considerations that go beyond the purely technical. The geological context of the find, the precise layer of rock in which it occurs, and its spatial relationship to other fossils in the same area, carries information about the depositional environment and the taphonomic history of the specimen that is permanently lost if the excavation is conducted carelessly. The orientation of the bones relative to each other, the presence or absence of articulation between adjacent skeletal elements, the nature of the matrix surrounding the bones, all of these contextual details can be scientifically valuable and must be carefully documented before or during removal of the material from the field. Modern paleontological fieldwork involves extensive photographic and three-dimensional digital documentation of specimens in the field, before and during excavation, to create a permanent record of the spatial context that will be lost when the fossil is removed from the rock. Photogrammetry, a technique that uses overlapping photographs to generate three-dimensional digital models of objects and surfaces, has become a standard field tool that allows the creation of accurate three-dimensional records of fossil positions and the surrounding rock surface in a way that detailed hand-drawn maps and notes alone could not achieve. These digital records become part of the permanent scientific archive of the find, available to any researcher anywhere in the world who has access to the institutional databases where they are stored. The laboratory preparation of fossils, the work of removing the surrounding rock matrix from the fossil material after it has been returned from the field, is itself a highly skilled and often extremely time-consuming process. For large specimens, the preparation work may take years, with preparators spending thousands of hours working under microscopes with tiny pneumatic tools and dental picks, removing rock grain by grain from around delicate bone surfaces without damaging the fossil material beneath. The standard of preparation work has improved enormously over the past several decades, driven by advances in the tools and materials available for the work, and by the growing recognition that well-prepared specimens retain more scientific information than hastily prepared ones. Once a specimen is adequately prepared, the scientific analysis begins. Modern analytical techniques applied to fossil specimens include the computed tomographic scanning we have already mentioned, various forms of spectroscopic analysis that can identify the chemical composition of fossil material, and sometimes distinguish original biological chemistry from the replacement minerals of diagenesis, scanning electron microscopy that reveals microscopic surface details not visible to the naked eye, and various forms of stable isotope analysis that can provide information about the diet, habitat, and physiology of the living animal. Each of these techniques has become more powerful and more accessible over the past 2 decades. And the combination of techniques that can now be brought to bear on a single significant specimen like the Carnotaurus holotype produces a richness of scientific information that would have been unimaginable to Bonaparte when he first described the animal. The scientific community that engages with this information is itself a global network of specialists who contribute different skills and perspectives to the analysis of fossil material. A paleontologist describing the skeletal anatomy of a new specimen may collaborate with a geochemist who analyzes the isotopic composition of the bones, a biostratigrapher who determines the age of the surrounding rock layers, a palynologist who studies the fossil pollen from the same formation to reconstruct the ancient vegetation, and a biologist who uses ecological models of living animals to generate hypotheses about the behavior and physiology of the extinct species. This collaborative, interdisciplinary approach to paleontological research is one of the defining characteristics of the modern era, and has been enormously productive in generating new insights about the biology and ecology of ancient organisms. The Argentine scientific institutions that play the central role in the study of South American Cretaceous dinosaurs, including the Argentine Museum of Natural Sciences, the CONICET Research Council, the Universities of Buenos Aires, La Plata, and Neuquén, and the various provincial museums that hold significant fossil material, are part of this global network, while also maintaining the particular connection to the material that comes from being the institutions of the country where the fossils were found. The relationship between Argentine paleontologists and their international collaborators has generally been productive and collegial, but it also reflects the broader tensions that exist in international scientific collaboration around the study of natural heritage, questions of intellectual property, institutional credit, and the responsibility of well-resourced institutions toward the countries and communities from which scientific value is extracted. These are not questions unique to Argentine paleontology, as we touched on in the Spinosaurus narration, but they are particularly salient in a field where the primary objects of study are unique, irreplaceable physical artifacts that can only exist in one place at a time, and that carry scientific value far exceeding their material worth. The management of these tensions, the development of collaborative frameworks that respect national heritage laws and national scientific institutions, while also facilitating the international collaboration that maximizes the scientific value of important specimens, is an ongoing challenge that the paleontological community continues to address through evolving norms and practices. The educational role of paleontology, and specifically the public communication of dinosaur science through museums and popular media and educational programs, is another dimension of the field that deserves recognition as a genuine scientific contribution rather than mere entertainment. The millions of people who visit natural history museums each year, who watch paleontology documentaries, who read popular science books about dinosaurs, are engaging with scientific knowledge in a way that expands their understanding of the world and deepens their appreciation of the extraordinary history of life on Earth. This expansion of public scientific understanding has value not just in itself, but in its contribution to the broader culture of scientific literacy that supports the political and social conditions in which science can thrive. Carnotaurus, with its immediately striking appearance and its fascinating scientific story, is an excellent ambassador for the public communication of paleontological science. The bullhorns alone are enough to stop most museum visitors in their tracks and create the moment of arrested attention that is the prerequisite for any deeper engagement with the science behind the appearance. From that moment of arrested attention, a good museum exhibit or a good popular science communication can build toward genuine understanding, toward an appreciation not just of what Carnotaurus looked like, but of what it tells us about the history of life and about the power and the process of scientific investigation. The children who visit museums and see mounted Carnotaurus displays, or who watch videos about dinosaurs and encounter the bullhorned predator with its stubby arms and its fast-running adaptations, are experiencing something that will stay with them in ways that are difficult to predict, but that are often profound. The sense of wonder that ancient life inspires in young minds is one of the most reliable pathways into scientific curiosity generally, and the path from dinosaur fascination to deeper scientific interest, and sometimes to scientific careers, has been traveled by a remarkable number of the scientists who now advance our understanding of the ancient world. The paleontologists of tomorrow are in some cases the children of today, who are encountering Carnotaurus for the first time in a museum or a documentary or a book. Some of those children will go on to study geology and biology and evolution, will spend field seasons in the dusty hills of Patagonia or the red deserts of Morocco or the tropical outcrops of Madagascar, will sit at microscopes and computer screens analyzing the evidence that ancient rock has preserved, and will add their contributions to the growing body of knowledge about the extraordinary life that this planet has produced. The wonder that animates that work begins somewhere, and it begins often with exactly the kind of encounter that you have been having tonight, with the story of an animal so strange and so real and so distant that simply knowing it existed changes in some small but genuine way how you understand the world. And that change, that small but genuine shift in understanding, is the gift that the ancient world has been offering to the curious for as long as there have been curious minds to receive it. The dinosaurs did not know they were leaving us a gift. The rock that preserved their bones did not know it was building an archive. But here we are, the beneficiaries of geological patience and evolutionary creativity and human curiosity, sitting in the quiet of the evening with a story about a bullhorn predator from the Late Cretaceous of South America, and feeling, if we let ourselves, something very much like gratitude for all of it. For the improbable existence of life in the first place. For the extraordinary creativity of evolution that produced among its billions of experiments an animal as magnificently strange as Carnotaurus. For the geological processes that preserved the bones of that animal in the rock of Patagonia. For the human curiosity that recognized them as significant and undertook the patient work of excavating and describing and analyzing them. For the broader community of scientists and educators and communicators who have built on that initial discovery to create the rich body of knowledge that is now available to anyone who wants to know the story of the bullhorn predator. And for the gift of time, this quiet time, to sit with that story and let it settle into whatever part of you is still awake and listening. The gift is there, waiting, every night, in the millions of years of history that the rocks of the earth preserve, and that the science of paleontology slowly reads. You only need to be willing to receive it, and you have been, tonight, willing. The story of Carnotaurus, the meat-eating bull, the bull-horned predator of Late Cretaceous South America, is complete for tonight. The animal rests in its ancient floodplain, in the quiet of a geological night that has lasted 70 million years and will last until the rock finally gives up the last of its secrets. The scientists are in their labs and their offices, working slowly and carefully toward the next piece of the puzzle. The museum holds the bones in its long, quiet rooms, and you, the listener, the wanderer, the inheritor of all this extraordinary history, can rest now too. Sleep, and let the ancient world be with you in whatever form dreams give it. The bullhorn predator moves through the warm Patagonian dark. The titanosaurs stand quiet in the river mist. The stars wheel slowly overhead, the same stars in different configurations, witnessing now as they witnessed then, patient and present and utterly indifferent to everything except the burning, which they do with perfect, committed devotion for billions of years, like the story of life itself. like the world that produced Carnotaurus, like the world that produced you, burning slowly and persistently in the beautiful dark. Good night. There are aspects of the Carnotaurus story that we have touched upon lightly, like a hand skimming the surface of deep water, and that deserve to be explored more fully before this evening's narration draws to its close. The night is still long, and the quiet is still with us, and the ancient world of the bull-horned predator has depths worth plumbing with care and patience. So let us go back, not to the beginning, but to the middle, to the living animal in its living world, and spend some additional time there, observing more carefully, thinking more slowly, letting the details accumulate with the gentle persistence of sediment settling onto a riverbed. The rivers of Late Cretaceous Patagonia were not the fast, cold, glacier-fed rivers of modern Patagonia. They were warm, slow, brown rivers, heavy with sediment, winding through a landscape of broad floodplains and occasional higher ground, fringed with vegetation that was an extraordinary mixture of old and new. The ancient ferns and cycads and horsetails that had been part of the world's green fabric since the Carnivorous, coexisting with the newer angiosperms that were expanding their dominance across the planet with the quiet, relentless efficiency of organisms that have found the right combination of features for the moment in which they find themselves. The rivers flooded seasonally, spreading their brown water across the floodplains in the wet months and retreating to their channels in the dry months, creating the cycle of inundation and desiccation that structured the ecology of everything that lived within their reach. Carnotaurus would have known these rivers intimately, as any large territorial predator knows the significant features of its home range. It would have known the crossings, the places where the water was shallow enough to ford without difficulty, and the deeper pools where large fish congregated in the dry season when the water levels dropped. It would have known the sandbanks where titanosaurs came to drink in the late afternoon, making themselves briefly and specifically vulnerable in the moment of lowering their enormous necks to the water surface. It would have known the patches of dense vegetation on the floodbanks where prey animals sometimes sheltered during the heat of the day, creating ambush opportunities that a fast predator could exploit if it approached carefully and silently from the right direction. This knowledge of landscape, this accumulated spatial memory of a home range visited and revisited across years and decades, is one of the cognitively demanding aspects of large predator life that is sometimes underappreciated in popular accounts of dinosaur behavior. Large carnivores in modern ecosystems maintain detailed cognitive maps of their territories, remembering the locations of water sources, prey aggregations, rival territories, and other ecologically significant features with a precision and a durability that reflects genuine learning and memory rather than instinct alone. If Carnotaurus had comparable spatial cognitive capabilities, and there is no anatomical reason to think it did not, then the mental life of an adult territorial Carnotaurus was richer and more complex than the instinct-driven automaton of popular imagination. The experience of the dry season would have been particularly challenging and cognitively demanding. As the floodwaters retreated and the floodplain grasses dried and the titanosaur herds began to concentrate around the remaining water sources, the competition for food resources would have intensified in ways that required the predator to be both strategically flexible and physically persistent. The most straightforward hunting opportunities of the wet season, when prey was widely distributed and relatively unwary in the open grassland, would have given way to the more concentrated but also more competitive opportunities of the dry season, when multiple predators were drawn to the same water sources at the same times, and the prey animals were correspondingly more alert and more defensive. The behavioral flexibility to adapt hunting strategies to the changing conditions of the season is itself a cognitively demanding capability, requiring the integration of current perceptual information, stored memories of past experiences, and something approaching planning or anticipatory behavior. Whether Carnotaurus possessed this kind of flexible, planning-oriented cognition is a question that the fossil record cannot answer directly, but the ecological demands of its lifestyle as a large territorial predator in a seasonally variable environment, competing with other predators for limited prey, create strong selection pressure for exactly this kind of cognitive sophistication. The brain of Carnotaurus, reconstructed from the dimensions of the endocranial cavity preserved in the skull, was not large in absolute terms relative to body mass, following the general pattern of non-avian dinosaurs that had brains significantly smaller relative to body size than modern birds or mammals. But relative brain size is only one dimension of cognitive capability, and the internal organization of the brain, the relative development of different regions associated with different cognitive functions, is equally or more important in determining what an animal can do with the neural tissue it has. The olfactory regions of the Carnotaurus brain appear to have been well developed, consistent with a predator that relied heavily on smell for prey detection and tracking. The regions associated with visual processing were also reasonably developed, suggesting adequate visual integration for the kind of pursuit-predation that the body plan implies. The paleontological study of dinosaur brains has advanced considerably in recent years through the application of computed tomographic scanning to theropod skulls, allowing the internal morphology of the brain case to be documented in 3 dimensions without the destructive cutting that earlier researchers had to employ. These studies have revealed that the brains of various theropod dinosaurs were more diverse in their internal organization than a simple scaling of brain size would suggest, with different lineages showing different relative development of different brain regions that reflects the different sensory and cognitive emphases of their particular ecological strategies. The abelosaurid brain, as studied in species with well-preserved brain cases, appears to fit a pattern consistent with strong olfactory emphasis and adequate but not exceptional visual and spatial processing, a combination appropriate for a large predator that hunts primarily by smell and that navigates a relatively open landscape. The olfactory world of Carnotaurus must have been extraordinarily rich and information-dense in ways that we, as a species that has traded much of our olfactory processing capability for enhanced visual and cognitive abilities, can only dimly imagine. Modern large mammals with highly developed olfactory systems, such as bears and wolves, experience their environment as a complex landscape of overlapping chemical signals that carry information about the identity, sex, health, reproductive state, emotional condition, and recent activities of every animal that has passed through the area in the preceding hours or days. A similar olfactory landscape would have been available to Carnotaurus, providing a continuously updated information layer over the visible environment that would have been indispensable for the daily business of finding prey, avoiding rivals, and locating potential mates. Imagine for a moment the olfactory experience of a Carnotaurus moving through its territory in the early morning. The air carries the cooling residues of the night, overlaid with the fresh scents of dew on vegetation and the morning exhalations of the river That particular smell of water and mud and green things that is recognizable even to human noses as distinctive and morning-specific. Beneath this general environmental smell, the Carnotaurus's nose, far more sensitive and far more analytically capable than ours, is parsing dozens of specific chemical signals. The trail of a titanosaur herd that passed this way 3 hours ago, the individual animals identifiable from their scent signatures, their direction of travel, readable from the gradient of scent concentration along the trail, their emotional state at the time of passing, inferable from the stress hormones present in their footprints, the boundary markers of a rival Carnotaurus territory deposited yesterday, the individual recognizable, the age of the markers suggesting recent patrol activity that means the rival is active and nearby, the scent of water ahead, a river crossing point, and beneath the general river smell the specific scent of several large fish in the deeper pool on the other side. All of this information, processed in a fraction of a second, shapes the next decision. Which direction to travel? How cautiously to proceed? What opportunities are worth pursuing, and what risks are worth avoiding? The conscious experience that accompanied this olfactory information processing in Carnotaurus, if there was conscious experience in any sense we would recognize, is entirely beyond our reach. But the information itself was real and was being used in ways that shaped behavior in very specific and consequential directions. This is cognition, not in the form of abstract reasoning or language-based thought, but in the form of the rapid integration of complex environmental information into adaptive behavioral responses. A form of intelligence that is genuinely impressive, even if it is very different from the form that we most typically celebrate in ourselves. The daily life of a Carnotaurus, experienced from the inside, was almost certainly not the pure, clean experience of a perfectly efficient machine moving through an idealized environment. Like all living things, Carnotaurus was imperfect, variable, subject to injury and disease and parasitic infection and the accumulated errors of individual experience. Some individuals were better hunters than others, more skilled at reading the behavior of prey animals, or more capable of the sustained speed needed for successful pursuit. Some were better at territorial defense, more effective at communicating their size and determination through the display of their horns and body posture. Some survived to old age, their bodies bearing the accumulated scars and pathologies of decades of a physically demanding life, while others died young, taken by injury or disease, or a rival that was larger, faster, or luckier. The individual variation within a Carnotaurus population was the raw material on which natural selection acted to shape the species over geological time. Those individuals that were better at surviving and reproducing passed their characteristics to more offspring, and the characteristics that conferred advantages in survival and reproduction became more common in the population over generations. This is natural selection, the fundamental mechanism of evolution, operating not as an abstract principle, but as the concrete, generation-by-generation process by which each individual's success or failure at reproducing contributed to the statistical properties of the next generation. Over millions of generations, this process produced the extraordinarily specific and distinctive body plan of Carnotaurus, from the bull horns to the vestigial arms to the running adapted hind limbs to the textured, tuberculated skin. Every feature of Carnotaurus, however strange it looks to our modern eyes, was the product of this process, of millions of generations of selection for features that, in the specific context of the Late Cretaceous Patagonian environment, contributed to the survival and reproduction of individuals. The horns were there because individuals with larger, more symmetrical, more impressive horns outcompeted those with smaller or less impressive ones in the competition for mates and territories over many, many generations. The vestigial arms were there not because they were useful, but because the genetic instructions for building arms, reduced though they were, had not been entirely eliminated by selection, which would require specific mutations in developmental genes that had simply not arisen and fixed in the population. The running legs were there because faster individuals caught more prey and escaped more confrontations with rivals and found more mates over the long sweep of evolutionary time. The particular combination of all these features assembled in one body in one species, in one time and place, is what we call Carnotaurus. And it is a combination so specific and so intricate that it could only have been produced by this exact process, this exact sequence of evolutionary events, in this exact environmental context. Change any significant element. Give Carnotaurus a different prey community, or a different climate, or a different set of competitors, and the evolutionary pressures that shaped it would have been different, and the result would have been a different animal. Carnotaurus was not inevitable. It was contingent, dependent on a specific history of environmental and evolutionary events that could, at dozens of junctures, have produced a different outcome. This contingency is both humbling and liberating. Humbling because it reminds us that there is nothing inevitable about any particular form of life, that what exists is not the only possibility, but one among many possible outcomes of the evolutionary process. Liberating because it suggests that the extraordinary diversity and strangeness of life as it actually exists, with all its Carnotauruses and its tube worms and its giant sequoias and its hummingbirds, is not the minimum possible life could have produced, but the maximum that the particular history of this planet has so far managed. And that maximum is already more extraordinary than we usually appreciate. The appreciation of life in its full diversity and strangeness, including the vanished diversity and strangeness represented by the fossil record, is one of the most valuable contributions that paleontological science makes to human culture. Modern biodiversity is remarkable, astonishing, worthy of our fullest protection and our deepest awe. But it is also only a small fraction of the total diversity of life that this planet has produced. A snapshot taken at one moment in a history that stretches for billions of years, and that has included forms and communities of organisms that we are only beginning to understand. The fossil record is the archive of that larger diversity, and engaging with it is to expand our sense of what life is and what it can be, in ways that make the present world, already extraordinary, seem even richer and more profound. The present world, rich as it is also facing a crisis that makes the study of the deep past more rather than less urgent. The sixth mass extinction, the ongoing loss of species at rates far higher than the background extinction rate of the geological record, driven by the activities of a single species in a geologically instantaneous period of time, is transforming the biosphere in ways that the fossil record can help us understand and contextualize. The mass extinctions of the deep past, including the end Cretaceous event that claimed Carnotaurus and its world, were followed by periods of recovery and diversification. But those recoveries took millions of years, and the diversity that emerged was not a simple restoration of what had existed before, but something new, shaped by whatever had survived the extinction and by the ecological opportunities created by the losses. Understanding the dynamics of these past extinctions and recoveries is part of understanding what the current crisis means and what its long-term consequences might be. The paleontological record does not provide simple comfort in this context, because the recoveries from past extinctions were long and the losses were permanent, with the species that went extinct in each mass extinction never returning in their original forms. But it does provide the broader perspective of geological time, the reminder that life has survived and diversified through challenges that dwarf anything that human activities have yet produced, and that the resilience of life over geological timescales, while it provides no guarantees for any particular set of species, including our own, is nonetheless real and demonstrable. The lesson that Carnotaurus and its extinction might offer to us, if we are willing to receive it, is not that extinction is acceptable, or that lost species will simply be replaced by new ones. The lesson, if there is one, is about the deep improbability and the deep value of what exists. The fact that every species alive today, including our own, represents the outcome of billions of years of evolutionary history, a history that could at numerous points have gone differently, and that in fact did go differently every time a species went extinct and was not replaced by any equivalent. The dinosaurs that were lost in the end Cretaceous extinction were not replaced by equivalent animals. The niches they filled were modified and partially refilled by different animals over millions of years. But the specific evolutionary histories and biological innovations that the dinosaurs represented were gone permanently. The world that exists today is richer in some ways than the world of the Late Cretaceous, with mammals and birds and flowering plants all diversified far beyond what they were in the Cretaceous. But it is also irrevocably poorer in the specific sense that the non-avian dinosaur lineages, with all their evolutionary creativity and biological distinctiveness, are simply gone. This is what extinction means in the deepest sense. Not just the loss of individuals or even of species, but the termination of evolutionary lineages, the permanent end of particular evolutionary experiments that were producing results we can only partially imagine from the fragmentary evidence they left behind. The abelisaurids, with their bullhorns and their vestigial arms and their pursuit predator body plans, were doing something that no other group of animals has done before or since. And when they disappeared in the end Cretaceous catastrophe, whatever further evolutionary experiments they might have run, whatever forms they might have produced in the millions of years of Cenozoic evolution that did not come to pass for them, were lost forever. We know Carnotaurus. We do not know what Carnotaurus might have become. This thought, like all the best thoughts that a long evening of reflection produces, is one that opens outward as you contemplate it, leading from the specific to the general, from the particular extinction of one lineage to the broader question of what it means to lose evolutionary possibility, to terminate the potential of an evolutionary experiment that was still underway. It is a question that is relevant not only to the past, but to the present, to the ongoing extinction crisis, and to the choices that our species faces about what kind of world we want to inhabit and what kind of world we want to leave for the species that will come after us. But these are heavy thoughts for a late evening, and there is a limit to how much weight any mind should carry into sleep. So let us set them down gently, the way you set down something valuable at the end of a long journey, carefully and with intention, knowing that it will still be there when you return to it. The questions will wait, the past will wait, and the deep time of the geological record, patient beyond any human measure, will still be there in the morning when the day begins again, and the curious mind is ready to continue its exploration of the extraordinary world that life has made. For now, let the story of Carnotaurus settle into the soft place at the back of your awareness, not as a lesson or a conclusion, but as an experience. The experience of having spent time with something ancient and strange and magnificent, something that reminds you of the depth and richness of the world you inhabit, and of the long, patient, extraordinary history that produced it. That experience does not require any particular response or any particular conclusion. It simply is, in the way that all genuine encounters with beauty and strangeness simply are, complete in themselves and valuable for their own sake. The bullhorn predator of late Cretaceous South America walked its floodplain for millions of years. It hunted and rested and competed and mated and died and was replaced by its offspring, generation after generation, in the slow, unhurried way of all successful species. The Titanosaurs lowered their enormous necks to the river and raised them again and moved on across the plain. The pterosaurs turned in their wide circles above the warm afternoon. The rivers moved toward the sea. And all of this, all of it, was real, was actual, was the world as it genuinely was, preserved now only in the bones in the rock and in the minds of the curious who seek to know it. You've been one of those curious minds tonight. That matters. That is worth something. The act of caring about the ancient world, of spending time with its stories and its animals and its extraordinary biological creativity, is itself a contribution to the culture of wonder and inquiry that makes science possible and that makes the future worth having. Rest now. The ancient world is safe in the rock. The story is told, and the quiet of the night, with all its patient depth, is yours to inhabit for as long as sleep is kind enough to take you. Good night. Dream of ancient floodplains and warm rivers and the improbable beauty of a bullhorn predator in the golden light of a Cretaceous afternoon. Dream of deep time and evolutionary creativity and the extraordinary privilege of being alive and curious in a universe that has been making wonders for longer than any mind can fully comprehend. And wake, when morning comes, into a world that is still, in all the ways that matter most, full of those wonders, ready to be explored, ready to astonish. There are still threads of the Carnotaurus story worth following into the night. Threads that connect this specific animal to larger patterns in the history of life and in the practice of science that are worth sitting with in the quiet space between wakefulness and sleep. One of those threads concerns the relationship between body size and predatory strategy, a relationship that has fascinated ecologists and paleontologists alike because it touches on some of the most fundamental questions in biology about energy, efficiency, and the constraints that physics places on the options available to living organisms. Carnotaurus occupied a particular point in the body size spectrum of predatory dinosaurs, large enough to take prey of substantial mass, including juvenile and subadult titanosaurs, but not so large that its speed and agility were significantly compromised by the structural demands of supporting extreme body mass. This is a familiar ecological position, occupied in modern ecosystems by animals like lions and tigers and large wolves, predators that are genuinely large by any everyday measure, but that are dwarfed by the largest animals in their ecosystems, and that depend on speed and strategy rather than overwhelming mass to bring down prey. The ecological literature sometimes describes this position as the optimal predator size for a given prey community, the size that maximizes the energy returns from predation relative to the energy costs of hunting, and Carnotaurus, at roughly 1 to 1.5 metric tons, was close to the optimal size for the prey community it inhabited. The energetics of predation are a fundamental constraint on the life history and ecology of every large carnivore, and thinking through those energetics for Carnotaurus helps us understand the rhythms of its daily and seasonal life with greater precision. A large predator must eat enough to meet its daily metabolic demands, which for an active, potentially warm-blooded or mesothermic animal of 1-ton mass would have been substantial, perhaps in the range of 20 to 40 kilograms of meat per day in periods of high activity. Individual hunting events that provide much more than daily needs are characteristic of large predators, which consume as much as possible from each kill and can survive on relatively infrequent large meals rather than requiring constant small meals. A strategy that conserves the energy cost of frequent hunting while accepting the risk of variable intervals between feeding events. The evidence from modern large predators suggests that successful hunts are actually relatively rare events relative to the number of hunting attempts, with most pursuit predators achieving success in something like 20 to 30% of serious hunting attempts under favorable conditions and far less in unfavorable ones. A Carnotaurus that attempted to hunt 3 or 4 times per week and succeeded once or twice would have been meeting its basic energetic needs, particularly given the large size of the titanosaur prey that each successful hunt would have provided. The intervals between successful hunts would have been managed through the physiological capacity for metabolic depression during periods of food scarcity that most large predators possess, slowing the metabolism and reducing energy expenditure during the lean periods between kills. The ecological footprint of a Carnotaurus population in the late Cretaceous Patagonian landscape would have been substantial. A single adult required a certain minimum territory to provide adequate prey, and a population of adults required a total landscape area proportional to the number of individuals in the population. Estimating population densities for extinct animals from the fossil record is extraordinarily difficult, but ecological modeling based on the prey biomass available in comparable modern ecosystems and on the energetic requirements of large predators suggests that large theropod predators like Carnotaurus were never common in the everyday sense of the word. They were almost certainly rare animals, present in low densities across large areas, their territories abutting but not overlapping, their encounters with each other regulated by the territorial behavior and display signaling that the horn morphology suggests. The rarity of large predators is a fundamental feature of terrestrial ecosystems that is sometimes underappreciated in popular accounts of prehistoric life, which tend to emphasize the dramatic encounters between predators and prey, without sufficiently communicating the actual frequency of such encounters in the daily life of the ecosystem. A modern African savanna landscape, for all its abundance of large carnivores compared to most of the world's ecosystems, contains far fewer lions and leopards and cheetahs per square kilometer than most people would imagine. And the actual encounters between these predators and the large herbivores they hunt are spaced by long intervals of mutual avoidance and parallel but non-intersecting movement through shared landscape. The late Cretaceous Patagonian landscape, with its much larger herbivores and its correspondingly larger minimum territory requirements for apex predators, would have been even less densely populated by Carnotaurus than the Serengeti is by lions. This ecological reality has implications for how we should think about the social and behavioral life of Carnotaurus. Animals that are genuinely rare and genuinely widely dispersed across a landscape have limited opportunities for social interaction, and the evolutionary pressure on their social behavior is correspondingly different from that on animals that frequently encounter conspecifics in their daily lives. For Carnotaurus, the most significant social encounters would have been the territorial boundaries with neighboring adults, the seasonal encounters with potential mates, and the early life social bond between mothers and offspring if parental care was practiced. Beyond these specific contexts, the daily life of a Carnotaurus was probably characterized by a considerable degree of solitude, not the loneliness of a social animal isolated from its group, but the self-sufficient independence of a solitary predator for whom the absence of conspecifics was the normal condition rather than an exception. The season of reproduction, when adults sought out mates and established the temporary social bonds of mating and possibly nesting, would have been a departure from this normal solitude, a period of heightened social complexity and behavioral intensity that required the full deployment of the display and communication capabilities that the horn and body morphology of Carnotaurus supported. The approach of potential rivals competing for the same mate, the assessment of potential partners for quality and compatibility, the coordination of mating behavior between animals that were otherwise territorial and potentially aggressive toward each other. These were the contexts in which the cognitive and communicative sophistication of Carnotaurus was most fully exercised. The timing of the breeding season, whether it was triggered by day length, temperature, rainfall, prey availability, or some combination of environmental cues, as it is in most seasonally reproducing animals, is something we cannot determine from the fossil record. In tropical and subtropical environments, some animals reproduce year-round, while others concentrate reproduction in specific seasons that maximize the overlap between the peak of juvenile growth and the peak of food availability. The seasonal ecology of the Patagonian Late Cretaceous, with its wet and dry cycles, would have created a clear annual rhythm of resource availability that likely entrained the breeding behavior of Carnotaurus to produce offspring at a time that maximized their chances of reaching the next critical developmental threshold before the most challenging season of the year. The eggs of Carnotaurus, like the eggs of all dinosaurs, would have been incubated either through active brooding, where a parent sits on or near the nest to maintain temperature, or through passive incubation in a nest of organic material that generates heat through decomposition, similar to the nesting strategy of modern megapods among birds. The choice between these strategies, or some combination of them, is one that the fossil record of Carnotaurus cannot directly address. But the comparison with modern archosaurs is informative. Crocodilians, the closest living non-avian relatives of dinosaurs, typically construct nests of organic material that provide some passive thermal incubation while the female guards the nest against predators. Many birds, the living theropod dinosaurs, actively brood their eggs. If abelisaurids had retained some form of the ancestral archosaur nest-guarding behavior, as seems plausible, a Carnotaurus nest would have been a formidably defended location, the attending adult capable of deterring most predators from approaching the eggs through sheer physical intimidation, if not actual attack. The hatchlings that emerged from those defended nests would have been small and vulnerable, but not entirely helpless. The precocial young of many modern birds and reptiles are capable of independent foraging shortly after hatching, and the young of large predatory dinosaurs may have been similarly self-sufficient relatively quickly, able to pursue and catch small prey on their own from an early age. The small size and different proportions of juvenile animals often allow them to exploit prey types and hunting techniques that are unavailable to adults, and young Carnotaurus individuals no larger than a large modern bird of prey in their earliest years, could probably have caught insects, small reptiles, and the nestlings and eggs of other dinosaurs, dietary items that would have been completely beneath the notice of an adult Carnotaurus. This dietary flexibility in early life, the ability to exploit small prey that is unavailable to adults, is one of the factors that may have allowed large predatory dinosaurs to maintain viable populations in environments where large prey was sufficient to support only a limited number of adults. The young animals, exploiting a completely different trophic level from the adults, were not competing with their parents for food, reducing the parental burden of supporting offspring after hatching and allowing more rapid population recovery after events that reduced adult numbers. It is an elegant ecological solution to the challenge of raising large predatory offspring, one that nature has found independently in multiple lineages of large predators. The broader context of the abelisaurid family in the global ecosystem of the Late Cretaceous adds another dimension to our understanding of Carnotaurus and its ecological significance. The Late Cretaceous was the final act of the Age of Dinosaurs, a period of remarkable ecological diversity and biological creativity that produced some of the most extraordinary animals in the history of life before being ended by the catastrophe of the Chicxulub impact. In the Northern Hemisphere, the final phase of this age was dominated by the Tyrannosaurs and the Ceratopsians and the Hadrosaurs and the Ankylosaurs, a fauna of large animals that was in many ways the culmination of the northern evolutionary experiment in large terrestrial vertebrates. In the Southern Hemisphere, the equivalent final phase was dominated by the Titanosaurs and the Abelisaurids and the ancient lineages of crocodilians and pterosaurs that had persisted and diversified in the isolated Gondwanan landmasses. These two great evolutionary experiments, northern and southern, Tyrannosaur and Abelisaurid, Ceratopsian and Titanosaur, were running simultaneously and in parallel on opposite sides of the planet during the final millions of years of the Mesozoic, each producing its own extraordinary fauna in its own isolated evolutionary context. Neither fully aware of the other, except where occasional faunal exchange through sea level changes or island chains allowed limited contact between the two worlds. The end Cretaceous event ended both experiments simultaneously. The asteroid impact, recognizing no distinction between the northern and southern evolutionary experiments in its catastrophic impartiality, and both the Tyrannosaurs and the Abelisaurids, the apex predators of their respective worlds, went down together in the same geological instant. What survives of both experiments in the birds that fill the skies of both hemispheres today is the genetic and morphological heritage of the theropod lineage that gave rise to them. Birds, though they do not have bullhorns or vestigial arms or the compact body plan of pursuit predators, carry in their bones and their biology the deep evolutionary heritage of the theropod dinosaurs, of which Carnotaurus and its relatives were a part. The wishbone that a chicken or a turkey has in its breast, the furculum that is a universal feature of birds, is the evolutionary transformation of the clavicle bones that were present in the theropod dinosaur ancestors of birds. The scales on a bird's feet are the evolutionary remnants of the scaly integument that covered the feet of theropod dinosaurs. The air sacs that make birds such efficient respiratory machines are the evolutionary modification of the pneumatic sacs that penetrated the bones of many theropod dinosaurs, reducing their weight while maintaining structural strength. These connections, these evolutionary continuities between the extinct theropod dinosaurs of the Mesozoic and the living birds of today, are not merely poetic analogies. They are genuine biological relationships, documented in the detailed anatomy of both groups and in the phylogenetic analyses that establish the specific evolutionary relationships between them. Birds are dinosaurs, specifically theropod dinosaurs, in the same sense that bats are mammals and dolphins are vertebrates. The classification is not approximate or metaphorical, but precise and well supported by an extraordinary convergence of anatomical, developmental, and molecular evidence accumulated over several decades of intensive research. This means that when you watch a heron stand absolutely still at the water's edge, waiting with infinite patience for a fish to come within striking distance, and then strike with sudden explosive precision, you are watching the behavior of a dinosaur. When you watch a falcon stoop from a great height at speeds approaching 300 kilometers per hour to strike a pigeon in midair, you are watching the hunting behavior of a theropod dinosaur. When you watch an ostrich sprint across an open plain at speeds of up to 70 kilometers per hour, its long legs covering enormous distances with each stride, you are watching a theropod dinosaur run in exactly the way that the paleontological evidence suggests Carnotaurus ran across the floodplains of Patagonia 70 million years ago. Dinosaurs are not extinct. They are all around us, in every bird that sings in the morning, and every raptor that soars on an afternoon thermal, and every penguin that porpoises through the Southern Ocean. This thought is one of the most surprising and most delightful insights that modern paleontology has produced, and it transforms the way that many people relate to the birds they encounter in everyday life. The crow on the fence post becomes more interesting when you understand that it is the evolutionary descendant of the same general group of animals as Carnotaurus. The sparrow scratching in the dust becomes more remarkable when you recognize it as a small, feathered theropod dinosaur, engaging in exactly the kind of opportunistic foraging that its non-avian theropod ancestors practiced in the Mesozoic. The world becomes slightly stranger and slightly richer, and considerably more interesting when you see it through the lens of evolutionary history, and recognize in the ordinary the extraordinary connections that deep time has woven into every living thing. This is the final gift that the story of Carnotaurus offers, and it is perhaps the most practical gift of all. Not just wonder at the ancient past, which is real and valuable in itself, but a heightened appreciation of the living present, a capacity to see the world around you with slightly more of its true depth visible. The bird at the window is a dinosaur. The scales on a lizard's back are the evolutionary heritage of hundreds of millions of years of vertebrate evolution. The tree in the garden is the product of an evolutionary lineage that predates the dinosaurs. The grass beneath your feet is a more recent evolutionary invention than the birds that eat its seeds. The world, when you see it this way, is not a static backdrop to human life, but a dynamic, historical, constantly evolving community of organisms, each one carrying within it the accumulated innovations of all its evolutionary ancestors, each one part of a story that is billions of years old and that is still being written today. Carnotaurus, the bull-horned predator of late Cretaceous South America, is part of that story. One chapter in an enormous book, a chapter that lasted millions of years and produced one of the most distinctive and memorable animals in the history of vertebrate evolution. The chapter ended, as all chapters do, but the book continues, and the story that includes Carnotaurus also includes you, here tonight, letting the ancient world fill the quiet space of a late evening with its extraordinary creatures and its improbable beauty. Rest with that knowledge. Let it be a comfort and a foundation. The world has been making wonders for a very long time. and it has not stopped yet. And you are part of it. Part of the same long story that included the bullhorn predator in the warm afternoon of a Patagonian Late Cretaceous. Part of the same community of life that has been experimenting and failing and succeeding and transforming itself on this planet for 3.5 billion years. You are, in the deepest sense, not alone in the universe. You have the company of all that long history, all that accumulated evolutionary creativity, all those billions of years of life finding its way through every challenge the physical world has offered. Carnotaurus was one expression of that life, magnificent and strange and temporary like all expressions. You are another, equally magnificent in your own way, equally temporary, equally part of the great experiment that life continues to run on this small, extraordinary planet. Sleep now. Let the ancient world recede into the comfortable darkness. Let the bullhorn predator walk into the warm Patagonian night and become part of the past. Again, part of the rock and the fossil record, and the scientific literature, and the museums, and the imaginations of the curious. And let yourself, for a little while, be simply present in the current chapter of the story, breathing quietly in the dark, held by the planet that has held all the life that has ever lived on it, from the first cells in the ancient ocean to the bullhorn predator of the late Cretaceous to the quiet, wondering, sleeping animal that you are right now. The story continues. It has always continued. And in the morning it will still be there, vast and patient and full of wonders, ready to be explored again. Good night. Before the night is fully given over to sleep, there is a quality of reflection that sometimes arrives in the late hours, a gentle turning over of the day's experiences and the evening's stories, a kind of soft reckoning with what has been learned and felt and imagined. This is not the sharp analytical thinking of the wakeful mind, but something quieter, something that moves like water through the landscape of memory and understanding, finding the low places and filling them gently, connecting things that the busy mind kept separate. In that spirit, let us spend a little more time with some of the quieter aspects of the Carnotaurus story. The aspects that are not about dramatic predation or extreme anatomy, but about the simple, continuous, day-to-day reality of being a living creature in a complex world. Carnotaurus drank water. This seems obvious, almost too simple to mention, but sitting with it for a moment reveals its significance. Every day, or every few days, the bullhorn predator of the Patagonian floodplain made its way to a river or a lake or a seasonal pool and lowered its strange horned head to the surface and drank, as all animals that need water to sustain their biological chemistry must do. In that moment of drinking, the apex predator was at its most vulnerable, its attention divided between the need to drink and the ever-present awareness of its surroundings, its head lowered toward the water surface in a posture that reduced its field of view and brought it physically closer to the waterline where crocodilians lurked. The behavior of modern large predators at water sources reflects this vulnerability, with lions and tigers typically drinking quickly and alertly, scanning their surroundings frequently, retreating as soon as they have satisfied their thirst. Whether Carnotaurus showed similar caution at the water's edge, we cannot know. But the ecological logic of vulnerability at the water is universal for terrestrial animals, and there is no reason to think Carnotaurus was exempt from the behavioral responses that vulnerability generates in modern large predators. The crocodilians of late Cretaceous Patagonia, while probably not a significant predation threat to a healthy adult Carnotaurus, would have been a potential hazard to younger or smaller individuals. And even an adult's caution at the water would have reflected the deep ecological programming of an animal that had evolved in a world where the water's edge was always a place of concentrated risk. The sounds that Carnotaurus made and the sounds that it heard are another dimension of its daily experience that we can partially reconstruct through inference and comparison. The low-frequency vocalizations of modern crocodilians, which use both aerial and aquatic acoustic signals for communication within and between individuals, provide a starting point for thinking about what sounds a large archosaur might have produced. The bellowing of crocodilians is one of the most primordially evocative sounds in nature, a deep resonant roar that carries across water and through dense vegetation with remarkable efficiency, and a similar sound produced by a Carnotaurus in a territorial display or in the context of breeding communication would have been one of the more extraordinary acoustic experiences available in the late Cretaceous Patagonian landscape. The soundscape of the late Cretaceous world more broadly was dramatically different from the soundscape of the modern world. The insects that provided the constant background hum of modern tropical environments were present in considerable diversity, but the particular species compositions were different, and the sounds they produced may have had a different overall character. There were no frogs calling from the river margins, because frogs, while present in the Cretaceous, were less diverse and less abundant than they are today. There were no mammalian calls beyond the occasional squeaking of the small nocturnal mammals that scurried through the undergrowth. The dominant large-scale sounds were those of the dinosaurs themselves, the movements of titanosaur herds through vegetation, the bellowing or calling of various species in their various communicative contexts, and the wing sounds of pterosaurs overhead. Beneath these, the river sounds, the wind in the vegetation, the rain on broad leaves in the wet season, and the constant insect background provided the acoustic environment within which the life of Carnotaurus was embedded. The tactile world of Carnotaurus, the physical sensations that the animal experienced through its skin and its internal body, is another dimension of experience that is completely invisible to the fossil record, but that was real and was important in shaping behavior and well-being. The warmth of sunlight on the textured, tuberculated skin, the coolness of river water when the animal entered to drink or to cross, the sensation of soft ground giving under heavy footfalls and hard rock requiring more careful placement of the broad-toed feet. The feel of large prey animals beneath the feet and between the teeth in the moment of a successful hunt. These sensory experiences were the moment-to-moment reality of being Carnotaurus in a way that no amount of anatomical analysis can capture. The pleasures and discomforts of the physical world, the warmth of lying in afternoon sun, the relief of shade in the heat of the day, the satisfaction of drinking after a long period without water, are not exclusively mammalian experiences. Modern reptiles, often thought of as emotionally simple or even emotionally absent, show behavioral evidence of seeking and appreciating thermal comfort, of avoiding painful stimuli with all the urgency of any vertebrate, of appearing to engage in something very much like playful behavior in controlled conditions. The idea that Carnotaurus experienced something of the physical world, some analog of comfort and discomfort, satisfaction and deprivation, is not scientifically unreasonable and may in fact be supported by what we know about the neurological basis of basic emotional states in vertebrates generally. The neurological basis of emotion in non-avian dinosaurs is another area where we can reason by phylogenetic inference from modern animals rather than observing directly. The basic emotional circuits of vertebrate brains, The systems that mediate fear, aggression, social bonding, and the seeking of rewards, including food and warmth, are ancient in evolutionary terms, present in fish and reptiles and birds and mammals in a form that shows clear homology across these diverse groups. The limbic system, which underlies many emotional responses in mammals, has evolutionary precursors in the brains of modern reptiles. And the brainstem systems that coordinate basic behavioral responses to reward and threat are even more broadly shared across vertebrate classes. If Carnotaurus had a brain that was organized broadly like those of modern archosaurs, as the evidence of endocast morphology suggests, then it almost certainly had the neural hardware for at least the basic emotional states of reward-seeking, threat avoidance, and possibly social attachment, even if those states were experienced very differently from the complex, language-mediated emotional life of a human being. This is not to anthropomorphize Carnotaurus, to project human psychological complexity onto an animal whose inner life was almost certainly very different from ours. It is rather to acknowledge the genuine biological continuity between the emotional and motivational systems of non-avian dinosaurs and those of modern vertebrates, a continuity that is grounded in shared evolutionary heritage, and that makes it more, not less, accurate to think of Carnotaurus as an animal with something like an inner life, rather than as a purely mechanical system responding to stimuli without any subjective experience. The inner life of Carnotaurus, whatever its precise character, was the lived reality of this animal's existence, the stream of experience that flowed through each individual's life from hatching to death, shaped by the physical world of the Patagonian Late Cretaceous and by the behavioral responses that millions of years of evolution had built into its nervous system. We will never know that experience directly. We will never know what it felt like to be Carnotaurus, to feel the ground under those distinctive feet, to see through those lateral eyes, a landscape that no human being has ever seen. But we can know something about the world that held that experience, the physical and ecological context in which it occurred. And in knowing that context, we move slightly closer to an appreciation of the full reality of a life that was very different from ours, but that was, in all the ways that matter, genuinely alive. The morning light on the Patagonian floodplain, in the Late Cretaceous, came slowly. The eastern horizon lightened gradually from the deep black of a clear night through the blues and greens of early dawn to the golds and oranges of the rising sun. And in that gradual brightening, the landscape that had been invisible in the night resolved itself into detail. The river silver in the early light, the distant titanosaur shapes moving slowly through the morning mist, the vegetation along the riverbank catching the first horizontal rays of sunshine and turning briefly gold before the light rose higher and the day began in earnest. Somewhere in this awakening landscape, a Carnotaurus that had spent the night resting in the shelter of a low bluff or a dense stand of tree ferns would have been stirring. The cooling of the night that had lowered its body temperature gradually compensated by the warmth of the rising sun, its olfactory system coming fully online as the morning thermal began to move air from the floodplain across its resting position, carrying the first news of the new day's prey movements and territorial boundaries. The eyes opened, lateral and wide, scanning the landscape with the automatic alertness of an apex predator whose survival has never depended on being surprised. The horns caught the morning light, pale and solid, above the deep-set eyes. This was the daily beginning of a Carnotaurus, unremarkable in its individual instance, occurring every morning of every year of an animal's decades-long life, accumulated into a pattern of daily experience so familiar that it became the baseline of existence, the condition of normality against which anything unusual would stand out. The morning was the same, and the morning was always slightly different, and the animal moved through both dimensions of that reality, finding its way across the Patagonian floodplain with the confidence of long familiarity and the alertness of a predator that could never afford to miss the unusual detail that might mean danger or opportunity. We leave it there, in the morning light, just as the day is beginning. Not in the dramatic moment of a hunt, not in the territorial confrontation, not in the specific event that would leave a mark in the fossil record, but in the ordinary moment of a large predator beginning another ordinary day in a world that will end 66 million years from now, in an instant of cosmic accident, but that for now is simply present and whole and full of the particular ordinary, extraordinary reality of life, doing what life does, finding its way through the world, one morning at a time. The story is told. The ancient world rests in its rock. And you can rest too, held by the same planet that has held all this extraordinary history, breathing in the same oxygen that has been cycling through the biosphere since long before the first dinosaur walked the earth. Part of the same great community of life that produced Carnotaurus and Majungasaurus and Baryonyx and Spinosaurus and Stegosaurus and every other extraordinary creature that has ever walked or swum or flown across the surface of this planet. You are connected to all of it, more connected than you usually have time to remember. And in the quiet of the night, with the ancient world still warm in your imagination, that connection is something to rest in, to be grateful for, to carry into sleep as a kind of company that the long, lonely dark could never quite extinguish. Good night and good rest, and may the morning bring you back refreshed to the living world, which is, in all the ways that matter most, as full of wonders as the world of Carnotaurus ever was. The morning arrives, as it always does, steady and indifferent, and full of possibility. The floodplain of Patagonia, empty now of the giant animals that once moved across it, holds in its rock the memory of those animals with perfect geological faithfulness. The rock does not grieve. The rock does not celebrate. It simply holds in its mineral patience the record of all that has lived and moved across its surface, waiting for the curious and the careful to come and ask what it means. We have been asking tonight what the bullhorn predator of the Late Cretaceous means. We have found partial answers in the anatomy of its skull and the proportions of its limbs and the texture of its skin and the ecology of its prey and the evolutionary history of its family. We have found partial answers in the story of its discovery and the science that has grown around it and the broader questions about life and extinction and evolutionary creativity that its existence raises. And we have found, perhaps most importantly, the understanding that partial answers to extraordinary questions are themselves extraordinary gifts, worth receiving with gratitude and carrying with care into the days and years ahead. The world is old. Life is older than we can truly comprehend. The history of both is written in the rock beneath our feet, in the DNA of every living thing, in the bones that paleontologists continue to pull from the earth with brushes and patience and the particular kind of love that comes from devoting a life to understanding the deep past. We are the beneficiaries of all that history, the temporary custodians of a present moment that will itself one day become part of the past that future curious beings study and wonder at. Carnotaurus, the bull-horned predator of late Cretaceous South America, lived its full and complex life in a world it could not have imagined ending. We live our full and complex lives in a world we struggle to fully imagine continuing. Between those two positions, there is the long, patient, extraordinary story of life on Earth, connecting everything that has been to everything that is, and perhaps to everything that will be. That story is with you as you sleep. It is with you as you wake, and it will be with you if you let it, as a source of wonder and of depth that the busy surface of daily life does not always make visible, but that is always there, always present, always ready to be returned to. Good night.